All right, well, let's get started. I hope you all enjoyed the evening yesterday, the scenery, the food, and the company. But we need to get started again. So, you've seen during the conference that a number of companies have sponsored us. That helps us all because it helps us to reduce the cost of the conference. And what we want to start the day with this morning is to give an opportunity to some of those sponsors to talk a little bit about their company, what they do, maybe type of expertise they're looking for, and so on. So we'll start with the first one by Infusion.
Good morning, everyone. It's a great pleasure to be here and talking to you all. My name is Ilya. I'm a research scientist at Infusion. And today I wanted to talk to you about unleashing medical innovation, how we get from ideas to clinical impact rapidly. So maybe to start off, a quick few mentions about who we are. So we're a company based in Munich. We consist of currently 41 people and mostly academics as well. So we have very close ties to academia and also like to publish and visit companies and conferences as much as we can around the world. So here you also see a photo of the whole team and also a photo of my colleagues and me at last year's MIDL in Zurich. So efficient R&D. Let me quickly give you a glimpse of our portfolio and what we work on. So we cover a lot of different things, starting, of course, from the basics, something like segmentation in CT, fairly standard. But then we also have use cases for robotics. We work on more complicated setups like 2D and to 3D registration. We also do computer vision, for example, SLAM and 3D reconstructions. We also work in intraoperative settings where we have surgery guidance in real time, in this case, for example, for biopsies using ultrasound. And then we also do a lot of registration, even multimodal ones, such as this one, where you can see a ultrasound sweep being registered to an MR image. We also do, for example, vessel reconstruction from ultrasound sweeps, and even the newest addition to our portfolio, thanks to my colleague Max here, is monocular depth estimation. So we do all of these things, and if you paid attention, you remember that we're only 41 people. So the question is, how do we get all of this done? And the answer is that we try to always keep a core of libraries in C++ to make them performant, and we always try to, whenever we work for customers and work on their projects, to bring back the expertise and add it to our toolkit. And from this toolkit, since it's written in C++, it's very performant. We also implement a lot of stuff in OpenGL, so you can run it on the GPU for even more performance. And on top of that, we can build different tools. So the foremost among them is the Infusion Suite, which is a GUI interface for easy experimentation, rapid prototyping, where you have access to all of our tools, just the whole range that I showed you before. And for more specific needs, we also have Infusion labels where, for example, here, the goal is to quickly annotate and manage imaging databases. We can annotate, in this case, you see, for example, a spine CT, but we also support ultrasound, MRI, 4D data. And the good thing about this is, since we have this SDK, you can easily extend it. You can write your own C++ plugins. So maybe a quick show of hands, who of you is confident using C++? Yeah, okay, a few people. But we got you covered. We also have a Python SDK. So you can also use all of these tools from Python, and you still get the same performance. Also running on GPU, and it's fairly easy. So here you see a quick use case where you can load data, manipulate it, write it out. And then, of course, since we work a lot with customers, they can use our tools and algorithms and expertise to quickly create a prototype and then integrate that into their own apps. So to give you a quick demonstration of how this looks like in practice, I thought we could talk about spine. So spine is a very rapidly growing market. Last year, it was estimated to be $13 billion and expected to grow at a rate of 5%. And this is just the medical device market that I'm talking about here. And in our work, we had a lot of customers who were facing problems in the surgical planning phase for spine. So for that, we developed a whole new suite of algorithms, but we were able to reuse a lot of what we already had in our toolbox. So I'm going to show you here a few demonstrations of what we have introduced in the last year or so. So starting on the left, we see a video of our new Spine plugin, where we have integrated all the capabilities that we have for machine learning model inference, rendering, visualization, key point localization, to create a new set of tools that lets you easily localize and segment vertebra with essentially just one click, since we had the in-house expertise for training all of these models. And then we could, of course, rely on all the tools that we had for, visualizing them in a nice way, making everything interactive. So here you can see how that would look like. And the cool thing about this type of data that we're showing is that you have a global orientation for the spine, but you also have individual orientations for each vertebra. So that lets you manipulate the whole mesh and allows us to do very precise mesh-to-mesh registrations, which we also already had. So we just had to kind of come up with the data type to make use of all of the algorithms that we already had. And in this case, I'm showing an example of how this would look like if you're trying to register the spine that you get from a patient to a template spine in this case. And you can even interpolate between them, and mesh registration, of course, being much more precise than just working on voxels. But it doesn't stop there. We can also reuse the same functionality within our labeling software, Infusion Labels. And we can even add a few twists. So here you see the UI of Infusion Labels, where you can also, with one button, localize all of the vertebra, which gets you started in spine projects very easily. And once you have them localized, you can, of course, manually intervene. You can remove vertebra. You can add new ones if you want. And once you have the localizations, you also see that they're all classified. So it will tell you which one is, for example, the L5 vertebra. And you can also segment them. You can even interactively work with the model by providing what we call hints. In this case, it's kind of like a conditional segmentation where you can say this was over-segmented or this was under-segmented, and the model will then reevaluate the segmentation and incorporate your hints. Or if you just want a quick start, you can also just hit segment all, and then you see that we, actually, yeah, that's coming up. We also segment the ilium and the sacrum, but here you see the segmentation of all the vertebra. And then, yeah, then you have a good starting point. You can still modify the annotations if you want, but this lets you really easily get up to speed if you're trying to create your own data set. But once you have your data established and also your, you've experimented a bit with your data and how you want to set up your pipeline using Infusion Suite, you can easily test it out on a bigger set of data using our Python bindings. So in this case, we also added Python bindings for the spine data types. And here you can see a very simple example where you load in some data, which is the first block. You can use the spine-based algorithms, which are also GPU accelerated, which is the second block. And then you can even get all of the information that is stored in the data, such as the vertebra orientation. And yeah, then you can just start from there and build in your own pipeline and try it out, how it looks on a bigger data set. As I mentioned earlier, we also do research. And one of the big issues that we faced when working with spine is the matching of the key points. So what you see here is one of the usual problems that you face. When you localize the vertebra, you get a set of points. So in this case, this is the image on the, I don't know if you can see my cursor, probably not. Yeah, so on the lower, the upper left, you see the key points. And all you know is the type of the key point. So you know, is it a vertebral body, left pedicle or right pedicle? But you don't know which set of 3 key points belong to the same vertebra. So the usual solution to this would have been something like Hungarian matching, which is very established and works well on healthy cases. But the ones that we're interested in are usually the pathological ones. So in that case, you often have false positives, as indicated by the red lines here, and also sometimes false negatives. So internally, we worked on a tool based on graph neural networks to solve this issue, and this will be a paper that we'll be presenting at MIDL this year, so look forward to that. But the cool thing about this is that going from research, we can actually, since we have all the capability for running machine learning models, we have all of the algorithms to work with spine, we have the visualizations, we can actually just drop this into our suite, and just make use of this. So the user wouldn't even know that something changed, but you get better performance all of a sudden. And just to reiterate the point of making use of what we have, since introducing this spine data type, which is this mesh-based spine with the individual vertebrae, we also started extending this concept to other organs, to other anatomies. Because as you all know, total segmentator is very popular in the recent months. So it's very easy to segment a wide variety of organs. And creating meshes from that, of course, leads to enabling us to also use the mesh-based registrations for those organs. So thank you for your attention. We also have a booth next door if you want to see for yourself how our products work. You can also just reach out to us if you're curious about anything. I'm here with my 2 colleagues, Max and Stefan, who are sitting here in the almost front row. And yeah, you can also get your own demo version online if you want. So thank you for your attention and hope you have a great rest of the conference.
Okay. Hi, everyone. Good morning. I'm Rajat, and I work as senior scientist in Merck Research Labs. First of all, gratitude to Vanderbilt University and MIDL community, you all, for giving me this opportunity to talk here about Merck. It's an honor and a pleasure. I also had this opportunity to talk about my poster yesterday, and some of the discussions were really interesting, but one thing that I found out is it's not common knowledge that we have an image processing team in a pharmaceutical company. We work dedicatedly on image processing projects. So I hope I can make that a common knowledge today and talk about what our company does and what is the structure in our company, what kind of data we get, and some of our projects that we have. So Merck, I'm sure you all know that it's more than 100 years old. We are known as Merck in US and Canada, but outside US and Canada, we are known as MSD. And in this 100 years, we have made several contributions that actually targeted the most prevalent disorders in the community. For example, Keytruda is a cancer immunotherapy drug. And then you have the Gardasil, that is the HPV vaccine, and Januvia that helps in insulin resistance treatment, and the Pneumovax, that is the pneumococcal vaccine. As we speak right now, we have 80+ programs in phase 2, 30+ in phase 3, and few under review. For those of you who are new to these terms, these are different phases in clinical trials. In phase 1, we usually test on healthy subjects, healthy individuals, and phase 2, we test on healthy individuals as well as individuals that are recognized with the target disease. And in phase 3, it's just a bigger group. And then under review indicates that we are through clinical trials and we are closer to an FDA approval. So approximately, we have around 69,000 employees as of December last year. We have our headquarters in Rahway, New Jersey, but we have many global locations where there is a lot of internal collaboration going on. We have imaging teams in Prague. We have image processing team in Singapore, and we work with them in many of our projects. So this is the organizational structure, but what I want to indicate here is we have a dedicated management representation for IT. So the image data analytics team fall under this IT group, but we support a lot of operations that happen in Merck research laboratories where the drug development takes place. And we also support a lot of projects in the manufacturing division and animal health. Let's talk about some of the works or in some of the ways we support these teams. In any of the drug discovery or development process, in the first few stages, what we do is we have to identify the target. A target can be some kind of a protein, or it might be something in the human body, or it might be something in a disease-causing pathogen that needs to be corrected or treated. A lead identification would be identifying that core molecule or the magic molecule that brings in the therapeutic effect. Lead optimization would be where we are trying to find the appropriate dosage so that there is maximum efficacy but minimum side effects. So in this process of lead and target identification, it's very common to use high throughput and high content screening. We are trying to identify, we are trying to work here with cellular images, trying to identify which is the best lead among all the molecules. Not just in image processing domain, we also work in generating protein structures using artificial intelligence. These days, there is a lot of protein structure generation models that are in the literature, and we do make sure that we capitalize on all these advancements in the scientific community. So after the lead and target identification, we have animal testing, where there is a lot of safety assessment process going on. We treat the animals with a particular drug and find out if it caused any kind of abnormality in any of the organs, let's say liver toxicity or a cancer effect in liver or something like that. We use a lot of histology data here. We work on models like anomaly detection, where we don't have enough annotations or information about the kind of abnormality, but we know how the normal structure looks like. And we also have other targeted histology projects like liver hepatotoxicity detection. And apart from the histology, we also have radiology data here, micro-CT and micro-PET. So this relates to the poster that I was presenting yesterday. In studies like reproductive toxicology, where we are trying to identify if this drug is given to a pregnant animal, will it affect the growth of the fetus in the pregnant animal? So towards the end of the pregnancy, we harvest the fetus, sacrifice the animal, harvest the fetus, and try to identify if there is any kind of abnormal growth in the bone or in the skeletal structure. So this is where we use a lot of micro-CT, micro-PET to identify skeletal abnormalities and all that. So once we are through preclinical stage, we enter the clinical phase, where we use a lot of MRI images, CT images, ultrasound to look into the safety assessment and the efficacy of the drug in human beings. So apart from the drug discovery pipeline, we also contribute to Merck manufacturing division, where we are trying to monitor the process using image processing. And we also try and find out if there are cracks in the tablet that's manufactured, or if there is any kind of observation that needs to be flagged. So all these operations are done in an automated way, where we contribute in building these models for the manufacturing division. We also work with the animal health teams, where we do plenty of video processing for monitoring and analysis purposes. So the image data analytics team actually falls under the data science group. The data science group is a group of around 40 people, and we have different divisions like NLP, bioinformatics, and representation learning, and we have the data science realization team. We collaborate internally and work on many projects together. Some of our representatives are working from Prague, and we're working different time zones. And there is a variety of data that we keep working on. Working in a pharmaceutical company helps us get different kinds of imaging modalities at the same time, and also work on data that we get from chemistry and gene signature, and improve our imaging models using all these prompts or additional modalities that we can fuse in the model. So the kind of techniques that we do develop in the team, I'm sure that many of you are familiar with all these techniques very well. Segmentation, classification, registration, object detection, localization. We work on a lot of histology data, as I mentioned. So the example that you're seeing here is where we are trying to remove the ink artifact, and not only that, also regenerate the tissue beneath the artifact. We also work on advanced AI/ML models, and the multimodality data fusion is a very unique factor, because being in a pharmaceutical company, again, helps us get this data from different teams, and we can use these models to actually get better decision-making models. So at this stage, I also want to talk a little bit about different projects that we are working on, just briefly discuss about it. If you're interested in these projects, we can certainly talk about it later. This project was about 3D lesion segmentation, and it was presented in ISB this year. So in this project, we had plenty of 2D annotations, but we wanted 3D annotations. So one thing that you will note, the common theme in all these projects is that we don't have enough annotations, but we have a lot of data. So most of our models work towards generating annotations or generating label data, and then building a bigger models over that. So here we trained the SWIN transformer, and we trained it using the contrastive learning. And once you have this pre-trained transformer, we try to develop our 2D and 3D segmentation models by fine-tuning the already existing segmentations. And the architecture looks like this. We have the encoder arm for the SWIN transformer, and we use the contrastive encoder to pre-train the SWIN transformer, and then we have the 2D and 3D encoder, which makes use of the feature maps from the encoder leg, and gives us refinement in our 2D and 3D segmentations for the images that we have. So the next project I want to talk about is the group equivariant GAN. This was published in ICLR 2020. And first of all, what is group equivariance? You know that when you're working with histology data, assume that you're working with nuclei data. Whichever way you rotate it, it should be the same label, right? If a nuclei is class A, then if you rotate the nuclei image, it should still be class A. It shouldn't be class B. And this is not very obvious to the neural network models. So what we do is, not when we perform convolution, we also rotate the kernel. Instead of just doing data augmentations, we rotate the kernel and generate stacks of feature maps, which are different variations of the same kernel. And then we continue this process until we have the stacked feature maps reduced to a single feature embedding. So if you look at this image, if you rotate it and perform the same operation, you're going to get the same feature embedding. So whichever way you're going to rotate the image, the feature embedding remains the same. We can talk more about group equivariant GANs, or you can even take a look at the paper or reach out to me later. But what I want to highlight here is that using the representations that we learned using the group equivariance, we were able to generate images that are much better than the existing state of the art. And once we know the labels, once we are generating images in a controlled way, we have a lot of label data, and we can build models accordingly. So the next project that I wanted to highlight here is the one that was published in MICI 2021, where we are using contrastive learning to perform segmentations on the heart images. And you can see that there are two tasks here. The task one is the contrastive learning task. Task two is the supervised segmentation. So we call it semi-supervised because most often we don't have enough annotations or segmentation maps for the data, and sometimes we don't have any at all. So what we do is we take a single image, we perform augmentations on the image, we generate two augmentations, and it's generated in such a way that they are very similar, but in contrast to a different sample in the data set. Now we have what we can call as positive bias and negative bias, and we train an encoder and we get all the parameters for this. And we use these parameters in the segmentation model, and we come up with the supervised segmentation. And we keep improving these parameters in an alternate fashion between the contrastive learning and supervised learning. And once we have a converged parameter set, we use that in our supervised segmentation. So the other project that I want to mention is something that was presented here yesterday in the poster. This is, again, the reproductive toxicology study where we are trying to identify if a fetus was affected by the drug that was injected to the pregnant rabbit. The main problem here is the bones in the fetus are not well calcified, so the density is going to be not what you find in the typical CT image. So any of the legacy segmentation methods or existing segmentation methods that you apply, you won't get the best segmentation possible. So what we did is we gathered the most successful segmentations in using the legacy methods, and then built a multi-atlas segmentation strategy using image registration. And once we have this method, we trained a larger data set. Each image using this method took around 4 hours. That's certainly not optimal. So we trained a deep learning model, which could actually give us the segmentations much faster and in a more robust way. You might also observe that a distance map has also been added during the unit training. This is because the bones that you see here, the focus for this project was the skull. And there are 22 bones in the skull, and they vary in shape and size. Some of these bones are very thin and very small. And in a label map, if you just have few ones and all zeros, it's very sparse, and the model is not able to converge that well. So what we do is we come up with the distance map, where the brightest spot is where the bone is existing. And the farther away we move from the bone, it gets darker and darker. And we use this to help model converge better. And we were actually able to get dice coefficients above 0.9 for most of our bone structures. So that's about the projects which I wanted to mention. I also want to briefly tell you that, assert again that we do have an image data analytics team in our company, and we do look for internships, co-ops. We do have interns already from Vanderbilt University. And our co-ops, internships, they are also open to international students. And working at Merck, you're definitely affecting how the medical field is growing, and you're able to contribute meaningfully. And because we have a good infrastructure, IT infrastructure, you always have the independence to try a lot of things. When you have a lot of data at your hand, you're able to actually build more advanced models, and you also tend to see more unique problems here where you can merge different modalities, and some of the problems that are not usually solved outside, you are able to solve it in this company. So definitely look us up. If you have any questions, please reach out to us. You can reach out to me directly to ask anything about the imaging team, or Antong Chen, who is the director of the data science group, and also an alumni of Vanderbilt University. Thank you.
Thanks again to our sponsors. We're going to get started with the technical component. One thing I would like to bring your attention to, there will be another VICE visit. So if you're interested in seeing ongoing projects with robots and so on, you can sign up. The tour will start at 10:30, and you can meet in front of the big screen there outside.
Okay, at this point, we're going to move to the next oral session. So we're going to set up for a second.
this one.
They'll introduce you. All right, when you're ready.
Welcome everybody to the morning session of the last day. My name is Maciej Mazurowski from Duke University.
And I'm Gustavo Rode from University of Virginia.
Yep. And we'll start with the first talk.
And we have our first talk on improving segmentation of objects with varying sizes in biomedical images using instance-wise and center of instance segmentation loss function. I believe the talk is being delivered by Fabian Rahmadi.
Yes. All right. Good morning, everyone. Thank you for coming here this morning for my presentation. So my name is Fabian, a special postdoctoral researcher at RIKEN in Japan, and I'm also a lecturer at the University of Indonesia, Faculty of Computer Science. So in this morning, I will present our paper titled Improving Segmentation of Objects with Varying Size in Biomedical Images using Instance-Wise and Center of Instance Segmentation Loss Function. So object segmentation in biomedical images is a common task. However, there are still challenges, especially due to the diversity of object sizes. And this problem is named imbalance problem. Now, there are two types of imbalance problem in segmentation task. The first one is class imbalance problem, where it happens when the number of pixels of a class is much higher than the other classes. For example, if we have small brain lesions versus a very large background. This figure shows how if we lose 1 pixel of a small instance, then the dice score will be affected much more than if we lose 1 pixel of a fairly large instance. So the second imbalance problem is instance imbalance problem. It happens when larger instances of a class dominates over smaller instances of the same class. So this figure shows that segmentation mask with and without deletion circled in the green here will have a similar dice score, which is around 0.98, but two different segmentation masks that differ in quality, especially in instance level, are hardly distinguishable in terms of dice score. So in this work, we focus on this second instance imbalance problem. So the main culprit of imbalance problem in the segmentation task is usually the loss functions, because most of them usually calculate the loss value based on the pixel level information, such as the true positive, false positive, and false negative. So let's say that we have a label image here in cyan with 5 different output or prediction images in magenta. And in here we have all of them have the same dice score, which is 0.9796. But we can argue that, especially on instance level, the P1 is the best predictions because it doesn't have any false instance and miss instance. Well, there is one single false prediction, false segmentation, but it is still included as, or we can say that it is still one instance, right? At the same time, we also can argue that P4 and P5 are the worst segmentations because they have one false instance and one miss instance. So if you look at other segmentation losses, then we also can say the same, like most existing segmentation loss functions such as focal loss, generalized dice loss, still fail to tackle the instance imbalance problems because they still calculate the segmentation loss value on pixel level. So if we want to solve the instance imbalance problem, we need a loss function that calculates loss value on instance level. And there is a recent work called blob loss where it calculates loss value on instance level. For each label instance, it calculates the loss value from each label instance and average over all these label instances. However, we felt that the blob loss is still not perfect, especially it still includes false positive that do not intersect with the instance of interest. So it is overly sensitive to the false positive. We will see the visualization later. So we proposed a new instance-wise segmentation loss function called ICI loss, which is a compound loss, consists of multiple terms. So in here, This is the instance-wise and center of instance, or ICI loss, consists of 3 different terms. The first one is L global, which is a pixel-wise loss function. Basically, it is just a segmentation loss. In this work, we tested by using this loss function, but it could be anything, your favorite segmentation loss. And then 2 new terms, which are our proposed instance-wise loss, or L instance, and then L center, the center of instance loss. So first, I will explain the main difference between the L instance of ICI loss and L blob of the blob loss by using these toy images of label image, where we have 5 label instances in cyan, and then output image which have several output instances in magenta. So first, let's focus on label instance number 3. Then we will have L instance something like this. So we can see that we only have 3 output instances that intersect with label instance, and we have 3 different color here. So the white one is correct segmentation, the magenta is the false segmentation, and cyan here is the mis-segmentation. Now, if we look at the L blob of the blob loss, there is another region here, the yellow regions, where technically they are the false segmentation from output instances that do not intersect with the label instance number 3. Now, if this process is repeated for all label instances, and then we can see the difference between the L instance and the L blob. If we look at the label instance number 2, which is the perfectly segmented by 1 output instance, we can see that the L instance is 0, right? Because it is perfectly segmented. That's nice. But if we look at the L blob, we can see that the L blob is 0.9. And then if we compare with the other label instance, for example, the label number 1, label instance number 1, which is not segmented at all, then it's very similar, 0.9. But if we look at the L instance, it is 1. So it's basically say that it is not segmented at all. Now, we can do this because we compute the connected component analysis, or CCA, for masking out output instances that do not intersect with the label instance of interest. In this figure is the label instance number 3. So the CCA is performed to both label and then output images, and then by doing that, we know the identity or the IDs of all instances from label image and output image. So for example, if we want to calculate the L instance of label instance number 3, then we know which output instances that intersect with label 3. Now, we use this information to mask out other instances that are not relevant to our L instance, and then we can calculate the L instance for this label L instance. Now, if we talk about the gradients usually comes from the output segmentation, and because in here, the CCA, the output of the CCA are used only for masking out the information, masking out instances that are not relevant to our computation, then the computation of the gradient is very easy. It's just like multiplication with the mask, right? So we have a multiplication, and then we can calculate the L instance. And this is just a fancy math formulation. Now, you might be wondering, what happens with output instances that do not intersect with any label instances? Well, technically speaking, they are calculated in the L global, right? However, remember that the biggest problem the instance imbalance problem is that we have multiple instances with different shape and sizes. So in here, we thought that, okay, how about we standardize the shape and sizes for all the instances, right? So basically, we don't have the instance imbalance problem from the start. So we do that by standardizing the shape and the size, and then based on their respective center of masses. And then we also can do this because we know the exact location for each or all instances, and then we can transform all instances, and then we can calculate the center of the masses. And then we can pick how big the size for all instances. And again, the gradient is still the same. It's just like multiplication of the mask, between the mask and then the output prediction. Now for the recap, again, we have 3 different terms, L global, L instance, and L center. And we also have weights for all these terms, A, B, C. We can just try different terms in here, and then this is the visualization of the ICI loss. Now, in experiments, we tested our ICI loss by using 3D residual unit from Monel library with sigmoid, so it is binary segmentation. For the dataset, we used the Atlas V2 challenge dataset for stroke lesion segmentation from T1 wasted brain MRI. The splitting is 600 training images and 55 validation images from open datasets, and then 300 hidden tests for the test. And then for the experiments, we tested our segmentation loss, ICI loss, by using whole image segmentation, patch-based, and patch-based segmentation. Now for the CCI itself, it's performed inside the loss function, so it's completed on the fly on the GPU by iterating the max pooling operation for several times. And then in this experiment, we used 400 operation. We can talk about this later. Okay. And then for the comparison, we tested by using the blob and then different weights of the ICI loss. Now, this is the performance in the test set that come from the Atlas V2 system. For the whole segmentation, we can see that by using all terms of the ICI loss, perform really well, especially if we have used these weights, right? And then this weight is technically just heuristically chosen because we believe L instance is more important than L global and L center, especially if we are dealing with multiple instances of, in here is the stroke lesions, right? And then the rank is technically comes from the dice score, volume difference, F1 score, and then simple lesion count, and technically we just rank different loss functions. And then for the patch-based segmentation, it's also the same. By using all terms of the ICI, we have quite or better rank than the blob loss, and then if we only use the dice loss. Now, the more interesting part is what happens inside the training and the validation. So here is the training curves. The purple and then the yellow here are the ICI loss. If we use all terms of the ICI loss, we can see that it produces a lower training curve of the dice loss. And then in here, we can see that it produces much lower number of missed instances in validation and also much lower number of false instances. So it keeps number of missed instances and the false instances lower, but at the same time, keeping the dice loss lower. Now for the conclusion, so our newly proposed ICI loss improved the segmentation of multiple instances with various sizes in biomedical images, and we tested on different settings. Whole image segmentation, patch-based segmentation, different pixel-wise loss function, different segmentation loss. It always improve the segmentation result, especially if we dealing with the imbalance problems, instance imbalance problem. However, we also acknowledge that ICI loss has a very similar limitation to the blob loss, especially because we need additional computational resources for performing the CCA. And then the ICI loss might be sensitive to the weights and hypermeter used. And in the future, we currently also developing detection loss from segmentation task, and then actually it is successfully developed, and then it also improved the segmentation, but it's still in the middle of experiments. Okay, that's all from me. If you are interested with our work, please come to the poster number 3, and then the loss function is now publicly available in the GitHub, and then you can try. Thank you very much.
Thanks very much for the great talk. We have time for a couple of questions.
Hi, thank you for your great talk. I have a question regarding you applied or evaluated this method or this loss for only binary segmentation tasks. Maybe what I understand, but if we use it for multi-class segmentation?
Right. We also, One thing that I can comment about this is that we also tried in the LITS datasets where we have liver tumor segmentation and then also the liver itself. So the way we can do that is just separate the channel. Separate the channel of the tumor, for example, because we know that, the liver tumor, because we know that liver tumor has like imbalance problem, so instance imbalance problem, and then calculate the ICI loss.
Okay, that means you were actually treating that as a two problem or same problem?
So we have, for example, segmentation loss for multiple classes, and then regulars by the ICI loss.
Okay.
Yeah, so I mean, basically the output of the ICI loss, we have like 3 different output of the ICI loss, right? And then technically we can just use the L instance and L center.
Okay, so I am asking about like, do we need to make any changes in L instance loss?
No, you don't have to. No, you don't have to. You just separate the channel of the object that you want to have to be calculated by using the ICI loss, and then it will automatically calculate the ICI loss for you.
Okay, but if there is some cases like for one object, we have more regions covered, like for example, several instances for one class, but for a few class there are like lower number of instances. For example, one instance, in that case, what will happen? Like you are actually treating all the instances similarly?
Yeah, as I said, you can just separate the channel and then calculate the ICI loss for one channel if you want to have like dealing with the instance imbalance problem in a channel. And then if you don't need it, like for the other channel, you don't have to calculate it. But you can also calculate it if you want to. So it's just like one channel. You have to separate the channel.
Okay, thank you.
I mean, in the PyTorch, you can just like separate the channels from the output, and then you can just calculate the ICI loss.
Okay, that makes sense. Thank you.
Yeah, thank you.
We have one more question.
Yeah, thanks for a great talk, and really good that you're here.
Yeah.
I have a question about the adaptation of the loss function. Usually, if you adjust your loss function, you can steer towards optimal performance on a certain metric.
Mm-hmm. Oh, yeah.
And I'm really interested to hear more about the fact that if you give away to B and C, that you are have optimal performance on the dice score. I would assume that for A is 1 and B and C 0, that would give optimal performance on the dice, because you're training on dice, right?
Right. So one thing first is that we also used like separate ICI loss. For example, only use the L instance and L center. We found that if we only use L instance or the L center, it didn't really perform well. So the combination of the L instance and then L center is the best option. Now, whether it will works best for a very specific segmentation task, then you have to find it. I mean, it might be different for every segmentation task. Yeah.
Thank you.
If that makes sense. Okay.
Yep.
Thank you.
Thanks very much. Let's thank our speaker again.
Okay. Thank you very much.
The second presentation in this session is GeoLS, geodesic label smoothing for image segmentation, presented by Sukesh Adiga Vasudeva.
Thank you for the introduction. Hi, I am Sukesh Adiga. I am a PhD student at ETS Montreal. This is our work. Geodesic label smoothing for image segmentation. Let's start with revisiting the image segmentation, where we associate image pixels with target objects, such as like organs or tumor, or it can be structures. Recent segmentation method uses deep learning method, which commonly uses cross-entropy objective function, where the ground truth one-hot encoding, ground truth annotation is represented in as one-hot encoding. This is one example of it, like where if you consider 1 pixel of green label, then the below is basically the different classes, and this is the likelihood, or you can call it as a probability of the target class. This is good, this performs really good, but there are some issues which we discuss. So let's start with an example. We have a image and a label. If you look at the zoomed image, if you consider a pixel inside the green region, green label, then this 1/0 label is good. But if you consider a pixel which is in the boundary, then there is some ambiguity in the label. So this may not be so good. So this 1/0 label basically doesn't capture the spatial relations in the image. And also it doesn't capture the class-wise relationship, which could be like this. We don't know. We'll see. Next, there are some existing method which tries to tackle this interclass relationship and a spatial relationship in the soft label, in the form of soft labels. For example, label smoothing, where it distribute target label to to the non-target class. For example, you can use a uniform label smoothing, where you distribute uniformly to the all the other class, non-targeting class. You can also do with a non-uniform way. For example, like you can use a Gaussian around the target label. So these methods are generally used in classification, which works well. But in segmentation, we also need a spatial relationship, which this method ignores the spatial relationships. There are some spatially aware methods, such as dilating label, soft labels, soft segmentation, SVLS. So let's look at one of the example, like spatial varying label smoothing, where it takes a small patch. For that, they apply a Gaussian filtering to obtain a soft label. This is good, but all this method relies on a target mask. So far, like this soft label uses as a target mask to generate a soft label, but there are this method ignores the image intensity information. So our research question is like, can we somehow integrate the image context information in the label smoothing process? How? Maybe we can integrate geodesic distance maps to obtain an image aware distribution, which can be added into the label smoothing process. Okay. Let's start with what is a generalized geodesic distance map or a distance transform. Let's look at this example. If you have some seed point, then distance between each pixel to this seed point, for a Euclidean distance, it grows gradually. Whereas in case of a generalized geodesic distance, it basically tries to capture the target region, and then it gradually grows. So if you put it in a mathematically, this is basically the shortest distance between between each pixel and all the seed points. So here we find basically this is the minimum distance between each pixel to the seed set. Then the first term is basically the Euclidean distance, and the second term is an image gradient. So basically it incorporates basically both Euclidean distance and image gradient information. And the gamma controls basically the balance between the geodesic and Euclidean distance. So, let's look at example of how to generate a geodesic map. For example, if you have an image and a label, then you can obtain a seed points like various techniques. Here we have used a skeleton. You can skeletonize a label to obtain a seed points. Then you can generate a geodesic distance maps like this. Then we invert this image to focus on the geodesic map with exponential operation. Similarly, we obtain this map for each classes. Then we combine with these things with by normalizing for each pixel to obtain a geodesic, our geodesic map. We then combine this with a label smoothing process as shown in the equation, where the first term is basically the 1-hot encoding and the second term is geodesic map, which captures the image over distribution. And alpha here is basically the smoothing factor. Let's look at some of the comparison between the soft label and our method. Let us take two example of it, two image. Then if you look at the close-up region, which is having a same mask but a different intensity, then we look at the class probability of 1-hot encoding, which remains same. Then the LS and the SVLS, which is basically the label smoothing and spatially varying label smoothing, which has same class probabilities because it comes only from the target mask. Whereas ours, we can see like a different soft labeling, which is because it comes both from the image as well as a target mask. Okay. Let's look at the result, like whether this works or not. Okay. We validate our method with two data sets. One is BRADS, and the second one is abdominal, which is a FLAIR data set. And we compared with cross entropy and soft label methods and a focal loss as well. And we validate with dyes, surface dyes, and Hausdorff distance. So this is the BRADS result. We can see like compared to the cross entropy and other soft label method, our method improves the dye score as well as the surface dye score. And it is equally competitive with SVLS in case of a Hausdorff distance. And we see similar observation in abdominal data as well. This shows our method is basically consistently improves the segmentation performance. Let's look at some of the qualitative results. This is an example of abdominal CT. So if you look at this yellow region, which is basically pancreas, so our method actually improves, minimize this misclassification error in this challenging pancreas region. So we have more results, which I'll discuss in the poster. And to conclude, we propose a geodesic label smoothing for image segmentation, which integrates image-aware distribution through geodesic map. And it captures an interclass relationship in soft label. And in terms of result, we have shown like it consistently improves the segmentation performance and improves mainly in the challenging regions. And our take-home message is like, including the geodesic label adds an image context to the label smoothing method, which can improve the performance. Yeah, thank you. And I'm open for the questions.
Thank you, and we have time for some questions. I do have one, actually, to start off. So it looks like this relies on a couple of assumptions, right? So you want to take into account the image itself, but in a specific way, right? And so it looks like one of those assumptions is that if a pixel is farther from the seed points, then it sort of belongs to the class less, right? Or
Yes.
is less likely to belong to a class.
Yes.
And the other one is that is based on intensity, right? Those assumptions, that they're reasonable, but they might not be valid in a lot of situations, right? Like you might have actually pixels that are far from the skeleton or some differently calculated seed points that are that you can be very confident actually belong to the object. So did you think of sort of classes of problems, right? And especially as it pertains to medical imaging, where this would be more applicable to, and some where it would not be?
Yeah, we have tried a couple of like seeding strategies. Like for example, you can use erosion, because usually like your boundary is kind of you are like not sure like whether it is a belongs to this class or other class. So we have tried with erosion, then random seeding, as well as the skeleton. What we observed is seeding is like the better for like in general, but if you have like any particular task, like which you are like targeting, then you can use other seeding strategy as well.
Okay. Go ahead.
Hi, thank you for your talk. Could you go back to the slide where you defined the geodesic distance metric?
Yes. Yes.
Well, the one with the integral on it.
Okay.
I was just curious, I guess. It involves minimizing this path integral over the set of all like feasible paths. I just glanced at your paper. I'm wondering like, what's the computational tractability of doing this? Because you're minimizing over the set of all feasible paths for every single pair of locations.
Yeah, actually we calculate geodesic map offline. So it's like a one-time computation because your label doesn't change. So, yeah.
Okay, so the minimization is pretty trivial to compute?
Yeah, I can say. Means there are like faster version of geodesic computation. You can use that. Here we have used, I think I have cited here probably, geodesic TK. So that one we have used. But yeah, you can use a faster version. There is a PyTorch version as well. If you use that, maybe we can like do it in on-fly as well. Yeah.
Thank you.
We have time for one more question.
Yeah. So the question kind of connects to what you just said. So if you computed one time offline, what happens during data augmentation, for instance, on the fly? If you have some aggressive data augmentations that change these properties about the image, or yeah, consequently the label, how would you handle that?
That's a good question. Actually, yeah, basically your intensity information changes, but underlying the annotation is still you have confusion, right? We are changing that part. We are not changing basically the, the input. So we are providing at the optimization step. So
like, for instance, if the image changes drastically with scaling, rotation, shear, many factors at the same time, would that not change these computation that you need to do?
Yeah, it will change if you are doing it in on-fly, but we are doing it like offline. And as well as we are not using like too complicated augmentation. Here we have tried only with rotation and flipping, those kind of things.
Okay.
So yeah.
Yep.
Thank you for the questions, and let's thank the speaker again.
Thank you. Thank you.
And we have our last talk of the session on joint breast neoplasm detection and subtyping using multi-resolution network trained on a large-scale H&E whole slide images with weak labels. I believe the talk is being delivered by Adam Casson. And we
probably put up all the slides onto the big screen. Oh, Lord. Sorry.
No, thank you so much.
Thank you for the introduction. I'm Adam Casson. I'm from Page AI, and today I'll be presenting joint breast neoplasm detection and subtyping using a multi-resolution network trained on large-scale H&E whole slide images with weak labels. So the motivation here is breast cancer has recently surpassed, I think, lung cancer as the most commonly newly diagnosed cancer in the world, with about 2.3 million cases globally in 2020. In the US alone, there's over 1 million patients that go through a breast biopsy per year. And I think it was estimated in 2023, in the US alone, there will be 300,000 new breast cancer cases. But breast cancer is, I think, nuanced and has different lesions of interest that can really determine how a patient is treated and the path going forward for them. So early detection and accurate diagnosis can improve outcomes. So in this work, the neoplasms of interest that we focused on were 6 different neoplasms, specifically ductal and lobular invasive carcinoma, ductal and lobular carcinoma in situ, and then also ductal and lobular hyperplasia, or atypical hyperplasia. And there are various other neoplasms of the breast that we didn't consider, like mucinous carcinoma or Phyllodes tumor, et cetera, et cetera. And you can see also an illustration here of some of the differences between, say, ductal carcinoma in situ versus the invasive form of that. So in this work, there's a few challenges. One is dealing with whole slide images. So whole slide images are very massive and cannot fit onto the current hardware that we have at the time. So we can't just load it up and push it all through a neural network at once. For example, they can be 100,000 by 100,000 pixels in size. And the typical workaround in the space is to basically break these up into small tiles. This is commonly done at 1 or even maybe multiple magnification levels. So that leads us to another challenge, which is what magnification should we use? And so, if we imagine tiling one of these images at high magnification, this could be very useful, especially when the cell morphology or cell arrangements are important. For example, differentiating between maybe just normal or benign tissue and neoplastic tissue, or some other of the subtypes. But high magnification can also exclude discriminative features in some cases. So for example, if you imagine you have a lesion of ductal carcinoma in situ or an invasive ductal carcinoma, at such a high magnification, we can lose all context of the architectural patterns. And it might be very difficult for the model to differentiate between the two. Another challenge is oftentimes, especially in the work that we did here, we have weak labels. And what I mean by that is, there's these vast data sets that are available, but oftentimes you might only have the clinical diagnostic report from the doctor that's available. And those clinical reports often correspond to a single specimen, which could be comprised of multiple whole slide images. And the findings in those reports, one may not be present in all the slides, and there can be multiple findings, which is pretty common in this case, and that means that the labels are not necessarily mutually exclusive. And at a certain scale, with these large data sets of like hundreds of thousands of whole slide images, getting dense annotations can be very expensive and prohibitive. Because you need like an expert pathologist to sit down and draw and annotate pixels for hours on end. So our work, I think, sits at an intersection between 3 different related research lines. One is around weak supervision. There's multiple instance learning. There's another weakly supervised framework, CLAM, that has become very popular recently, as well as pseudo and automatic labeling. There's some work in, for example, in Gleason grading of prostate biopsies, that used some, looked at like homogeneous Gleason grades in order to improve their automatic labeling. And then also multi-resolution solutions for whole slide imagery. So our proposed framework consists of 3 stages. And the goal here is to effectively be able to subtype, create like a subtype segmentation of those lesions on the whole slide image, and also produce a slide level prediction regarding what lesions are present in that image as well. And our goal is to do this only from those case level or specimen level labels that we extract from the clinical reports without needing to do dense annotations from a pathologist. And so there's 3 main stages here. The first stage is this single resolution CNN. And so this is a network that its main goal is to differentiate between neoplastic tiles and normal tissue tiles. And then using that, that helps us do some pseudo-labeling so that we can then have a second stage, which is composed of a multi-resolution network of multiple convolutional networks and a lightweight transformer. And that goal is to assign a specific label to each of the tiles given that multi-resolution context, so that we can get this somewhat coarse segmentation of the subtypes. And then the third stage is using stage 1 and stage 2 as feature extractors in order to get these embeddings of all the tiles in the image, and then have a small lightweight neural network to aggregate all those embeddings and produce a single slide level prediction. So that first stage is that single resolution neural network. And so again, the goal of that is to differentiate between neoplastic tiles and normal or benign tiles. And so the way we train this is using multiple instance learning. And so multiple instance learning, for example, is we would have our network of choice. For example, we used SE-ResNet 50. And we push through all the tiles of a slide through that network. And we get out some tile probabilities of belonging to a certain class. And then what we do is we take basically the top K tiles in terms of their probability, and compute the loss between that and the case level label and backprop on that. Once that's sufficiently trained, we actually leverage that then to help us out with pseudo labeling to create like a tile level data set that has labels at that tile level instead of just at the case level. And in order to do this, imagine we have our whole data set of n amount of cases, and each one has a set of labels that we extracted from the clinical report. We filter this down and to select only cases with a single label. For example, case 2 and case N here only have a single label, so case 2 is invasive ductal carcinoma, and case N is ductal carcinoma in situ. And then we take those cases and then run that through our now trained detection network to get kind of a coarse segmentation of the tiles that are neoplastic. And because those cases only have a singular label, we can reasonably assign that case level label to all the tiles and create this large tile level annotated data set that way. We use that data set to train our subtyping network. And so the goal now of this network is to produce a tile level prediction of the specific subtype. So for this, we extract tiles at 4 different magnification levels, specifically 0.5 microns per pixel, 2.0, 4.0, and 10.0 microns per pixel. And so the objective here is to classify that highest magnification tile, the 0.5 micron per pixel tile, given the context of the other resolutions. And so our network here is composed of 4 different SE-ResNet 50 networks, each one kind of specializing in the resolution that is given. And we extract the embedding from those and then kind of concatenate them into a sequence of length 4 with positional embeddings just to denote what magnification each one is. And then that goes through a very small, lightweight transformer just to use the self-attention to mix magnification information. And then we can use that to create like a single embedding that we then classify into one of the subtypes. The third component is this aggregator network. So its input is 2 streams of tile embeddings. So we take the detection network and use that as a feature extractor to take all the embeddings from all the tissue tiles in the slide, and then the subtyping network we also do feature extraction on, but that's only on those tiles that the previous detection network detected as neoplasm tiles. And then in the paper, we tested out a bunch of different architectures, but the common theme was really just like these 2 streams with some sort of attention pooling to create, and then concatenation to create a simple slide level embedding. And then the objective here is just multi-label binary cross entropy to get that slide level prediction. So our data that we used was an in-house data set of slides from Memorial Sloan Kettering Cancer Center. And it consisted of 125,000 whole slide images from 54,000 specimens. And then we also had 188 slides with pixel level annotations that we used, some of those for operating point selection, and then some of those for evaluation. So because of the nature of this system, I think there's 2 ways to evaluate this. There's the segmentation evaluation, which we used 105 of those slides with dense pixel level annotations to evaluate on. I did some comparisons between using only the single resolution network versus the multi-resolution network. And then there's the specimen level predictions from the aggregation network. And for that, we had a test set of 2,000 specimens, which was about 8,000 slides that we used. So for the segmentation results, we have a dice plot here showing the single resolution detection network and the multi-resolution subtyping network. And so it seems that once we include the multi-resolution information into that network, we can bump up the dice score by about 10 points here. And so we can look at some of these heat map or annotations here. So what we have is the whole slide image thumbnail, or just like, very zoomed out version. The ground truth from a pathologist, and then the detection network is S1, and then the multi-resolution subtyping network is S2. And you can see in both of these cases that the multi-resolution information allows the network to really outperform the single resolution. And so we can look at a few other examples here of good examples. But then we can also look at a few that are not as good. I think these were randomly selected from the test set. And then there was a couple interesting failure cases just to understand where this would go wrong. And so here we have the dice of 0, so our network didn't predict any presence of a neoplasm here. And you can see that the annotation here, it's a very small lesion, so it might be failing to pick up on that. Another interesting failure case that was very low, dice of 0.18, was this example, and I think we had a pathologist look at this, and the thing that it over-segmented on is actually like a change to the tissue caused by the actual biopsy, and that causes some changes to the tissue there that might appear to look more similar to cancer. We also investigated the role of the resolutions in the subtyping network. And so what this plot shows is an example of a slide with ductal carcinoma in situ. And you can see the annotation here from the pathologist on the far right. And then what we're showing here is the network. We trained a couple variations of it with different resolutions included. So the first network is a single resolution, only getting that 0.5 microns per pixel tile. The second figure is showing when we have 0.5 microns per pixel plus 2.0 microns per pixel. And then the third is showing when we include all 4 resolutions, where the blue pixels here are like a tile level misclassification versus a correct classification. And then for specimen level detection results, our system was able to show that it improved over like a single resolution, weakly supervised multiple instance learning baseline by quite a bit, and achieved AUC of greater than 0.93 for each of the neoplasms that we focused on. So in conclusion, we proposed a framework that achieved accurate subtyping, segmentation, and detection while only requiring those clinical reports and labels from those for training. Additionally, we were able to deploy this in a new product from Page, that is the Page Breast Suite, and so a version of this system is actually deployed and in production with CE mark in the EU, UKCEA in the UK, and research use only currently in the US. And so I think our poster is 26. So would love to chat with more people at our poster this afternoon. Thank you.
Thanks for a nice talk. We have a question, time for a quick question or two. So while we wait, I have a couple of, well, actually starting from the last one. Like you demonstrated a few cases where the DICE score wasn't as nice as you would hope or expect or want to use. For these failure cases, do you have a algorithmic or mathematical understanding as to what went wrong in your solution architecture, and more importantly, what you need to do to improve?
Yeah, that's a good question. I think some of these we'd probably have to investigate more. I think, you know, like for one of those cases, we did determine that the likely cause was like this biopsy site change that caused the lesion to kind of give off this false positive, which I think has, you know, even for some pathologists that might be a little confusing at first. And so I think trying to understand why that is, you know, is going to require a little more sitting down with pathologists and trying to understand, you know, is it reacting to something that is confusing also to the human eye, or is there other things that are going wrong with it?
We have a couple of questions from the audience.
Hey, thank you for your talk. I have a question, maybe I missed that. So you said you train your model with cases that have only one label. For example, if there is invasive and in situ lesion, then you train with only one of those. The question is, how does it work then at test time? Did you also test it on cases with only one label?
Yeah, so the training on one label was only for this subtyping network, which at a time, you know, only sees a single tile. But at test time, we can use that on cases with multiple labels. But because it's only focused on a single tile, it generalizes pretty well. And so I think some of the segmentation results that we have, a lot of those lesions or a lot of those cases actually have multiple lesions present in them.
Okay, but then in the AUC values that you show in your last slide, are those evaluated on cases with multiple labels also?
Yes, yes.
Okay, and what label did you pick as the representative per slide then?
So this is both labels, so it has to, you know, accurately predict both of those at test time.
Okay, thank you.
question.
Yeah, very great talk. Thank you for sharing. So I'm wondering, in your pipeline, you like design as a multiple stage, right? So what do you think of the benefits of multiple stage design, or it is promising to design the model as a single stage for the whole pipeline?
Yeah, that's a good question. I think doing a single stage would probably be less intensive in terms of all the orchestration that has to go into training this. I think the issue right now was the lack of dense annotations, and the idea that we had was like we kind of already had this really good model at the single resolution, and we're looking to take it to that next level. And so I think that's what led us to the solution that we had. I think if we were able to achieve this at with a single model that was able to do this, I think that would actually be more ideal, and just cut down on the complexity of the system.
Thank you.
Yep.
Our last question.
Hi, thank you for the talk. So actually my question is a bit complementary. What is the actual benefit of the last stage of the pipeline, and did you try to actually infer the whole slide label directly from the output of the second stage as a map of classes?
Yeah. Sorry, could you repeat the...
because you have first output, which is a map of each classes for each patches on the whole slide. And from this, can you infer directly the whole slide label, the diagnosis? Why do you need the last stage where you do the whole slide aggregation?
Yeah. So the last stage there for the whole slide aggregation, I think is also there, or I think one component is thinking about like the product that this was intended to be in, and I think the idea really was to start out with just that whole slide label, and then using hoping that the segmentation maps would get better with time. And so being able to have that as like the main interface with what like a pathologist would see, I think was important to us.
Okay, thank you. Thank you.
Yeah.
Thanks very much again for the great talk.
Thank you.
And thanks to all the speakers, and thanks to my co-chair from Duke University as well, and I think our session is finished.
Yep. So that concludes the oral session. I know one of the chairs has to catch a flight, so they're about to leave the stage. But we actually have teaser talks for a few minutes, and then I have some announcements, and then we'll go to posters. So I'm sorry that I'm standing in between you and coffee, but if I could have all the teaser presenters up at the right here. And yes, many of them are from New York, and thus it's like a lot of people. Okay, our first teaser talk is P055.
Hi, I'm Léo Mileki, PhD student at Paris-Saclay University, and I'm looking forward to presenting and discussing with you our work called MIDL, 3D medical images with clinical prompts from limited tabular data for renal transplantation, where we use multimodal contrastive learning to learn meaningful representation of renal transplant MRI data, incorporating clinical and biological information by leveraging textual data and large language models. So I will be at poster 22 and looking forward to discussing with you.
Our next speaker is P121.
Hi, I'm Sofia. I'm from the University of Porto, and my paper examines how the way a chest X-ray is performed can impact deep learning models. So the gold standard way of doing it is with the patient in a standing up position and the beam transversing the patient from back to front. But sometimes that's not possible. For example, if a patient is too ill to to stand up. So in that case, the scan is performed in a lying down position, and the beam traverses the patient from front to back. And this difference in projection can really affect the way anatomical structures look in the scans. So from here, the question is, are deep learning models really learning to classify pathology, or are they actually learning if you are too ill to stand up, basically? Just learning if you're standing up or lying down, and making decisions based on the wrong information. So if you want to know the answer, visit me at my poster. Thank you.
Our next speaker is P110.
Hi, everyone. My name is Leon, and in this work, we took a look at diffusion MRI. So this is a really cool modality that allows us to do this thing called tractography. We can track through the brain and estimate these white matter fibers. But a problem with this is that these types of data are often collected in a research setting. They're not collected clinically. It really limits the amount of the populations that we can investigate with these cool techniques. So on the other hand, though, T1 weighted MRI on the bottom is very commonly collected brain MRI modality, collected both clinically and in research, and of course has a large scope of a lot of patient populations. So our question was, can we do this tractography analysis just from the T1 MRI without the diffusion? And so we proposed this new spin on convolutional recurrent neural networks to investigate that. And if you want to talk a little bit more, come hang out at W14. Thanks.
Thank you, Dr. Kai. Our next speaker is P128.
Yeah. Hi, everyone. I'm Alexei Bashkanov from University of Magdeburg. So in this work, we looked at multimodal fusion of image and tabular data. So this tabular data are quite often overlooked, and we tested several methods to fuse them. Yeah, there are some advanced methods to impute this tabular data into the image features in the model. And we also looked at so where is the best location for doing this. And we also looked at how do we include PSA prostate-specific profiles in this framework, because these data are sequential and we reduce it to tabular formulation. So if you are interested, come to me at T22. Thank you.
Our next speaker is P136.
So hello, my name is Roel van Echten. I'm a PhD candidate at Amsterdam University. For my work, I work with coronary CT angiography images, and next to your standard CT artifacts that you'll have for CT acquisition, with angiography contrast administration, we have the extra issue that we only have a very slight time window where the contrast is actually optimal to do nice diagnosis of these images. And often enough, scans will be acquired not within this optimal window, and that will then typically decrease diagnostic accuracy. So for my work, I looked into whether it's possible to retrospectively adjust the contrast in these suboptimally acquired scans with the knowledge that we have from these optimally acquired scans. So we can add a bunch of constraints in generative adversarial networks to actually allow us to do this. So my poster will be in the room over there. If you have any questions, please come by. And yeah, so let's have a talk.
Our next speaker is P143.
Hi everyone, my name is Devesh Shah. Today I'm going to present our paper, and in my poster, it is called poster 17, P17 here, where I'll present our transformer-based network, and where we have tested it across 8 data sets. So colonoscopy or colon cancer is considered as the second leading cause of cancer in both male and female. So it is also called equal opportunity cancer for both male and female. and there is a high miss rate of around 25%, which means like 1 out of 4 diagnosis is usually missed by endoscopists. So here we try to solve this problem with the help of machine learning-based technique and with the transformer-based network. So I invite you, all of like ladies and gentlemen, as it is an equal opportunity cancer, to my poster at P17. Thank you.
Our next speaker is P162.
Hi, everyone. My name is Matthias Keicher from the Technical University of Munich, and I'm happy to present our work on few-shot classification of chest X-rays. So the core motivation is that recently it has been shown that these contrastive pre-training with radiology reports and chest X-rays is highly effective in creating representations that are useful for zero-shot classification, but it has mainly been shown for common pathologies like check spread labels. But what we found is that this is actually not the case for more detailed clinical findings that are required for tasks like structured reporting, for example, localization or severity estimation of diseases. So therefore, we propose a method that builds on the initialization from zero-shot classifiers and further improves the embeddings using only a few high-quality annotations. So if you're interested in application of vision language models in this domain and structured reporting, visit me at poster 19 on this side. Thank you.
Our next speaker is P204.
Good morning, everyone. I'm Molin from MIT. Now I'm a PhD student there, working with Professor Alvarado Stenson. So this work, we are working on zero-shot self-supervised reconstruction for MRI from measured signal. And what's the difference between our work and the current existing self-supervised reconstruction? The first one is the data. We are using a time series MRI data instead of a single image. And the second one is like we explore the temporal correlation and incorporate that to the framework. And the third one is like our framework is very easily to be extended to the estimation of sensitivity map. So we can actually do in a joint estimation of MRI images and the sensitivity maps. If you are interested in that, welcome to discuss. We are located at 21. Thank you.
Thanks, Mullen. Our next speaker is P237.
Hi, everyone. My name is Owen Crystal. I'm a master's student from Toronto Metropolitan University. So my work is on domain adaptation using silver standard mass for lateral ventricle segmentation in FLAIR MRI. So as we know, when we test on data that's out of distribution, you commonly see a drop in performance. So what we do here is we propose a novel, unique pipeline that essentially addresses that using silver standard mass, and we get great performance, and we really don't see that drop in performance on out of distribution data. If you want to discuss further, you can visit me at W23. Thank you.
Our next speaker is M08, or 018.
All right, hi, everybody. I'm Nalini. I'm from MIT. And so in this project, what we were trying to understand is what the core layer structure should be for neural networks that are used for different MRI reconstruction tasks. So the goal here was not to design a state-of-the-art architecture for any specific task, but rather to understand sort of what's a really modular, flexible drop-in layer that we can use across a variety of architectures. And so the key idea that we came up with is that it's really useful to use convolutions both in Fourier space and in image space. So we proposed 2 layer structures that combine both of these, either in series or in parallel. And we show experimentally a couple of things. So first we show on a bunch of different types of reconstruction tasks, including undersampled reconstruction, motion correction, and denoising, that really simple networks that are comprised of these types of layers do well without sort of any architectural bells and whistles. And then for the undersampled reconstruction case, which has been pretty well studied, we show that you can use our layers in conjunction with a lot of architectural features that people have developed elsewhere. So you can use them in combination with data consistency constraints, and you can drop in our layer as sort of a replacement for the image space convolutions in unrolled networks and get improvements in performance and in training time. So if you're interested in that, come talk to me at, I think the poster number is actually 45, and this is the paper number. Thanks.
Great. Our next speaker is S055. F017.
Doesn't matter.
Yeah. A different poster number. Yeah.
Hi everyone, my name is Robin Lomans. I'm from the Radboud University Medical Center in the Netherlands. Have you ever wished for a faster annotation process for medical images? I'm sure many of you have, and we can totally relate. So in our project, we've been working on improving the annotation efficiency of tumor cells in diffuse gastric cancer. And we do this by implementing a interactive object detection framework and show that it substantially reduces the annotation efforts required to annotate these images. So if you're interested and curious how we tackle this need for speed, then come by our poster. We're number 32 right over there in the afternoon. Thanks.
And our final speaker is S091.
Hi everyone. So it's a short paper and still very much work in progress, but here we discuss and study interesting and unexpected properties of the dice loss and other variants of the dice loss. So if you happen to use the dice loss, please come see me. We'll be by the window with a flashy shirt. Thank you.
So a few announcements. I'm fairly certain that several of you are standing there and have not presented, so that means either I didn't receive your short talk or there was some error. We will try and make this up at the end of the last oral session. Also, if you would like to go on the VICE tour, the last VICE tour will be meeting out at the Vanderbilt, I don't know what to call it, but banner in the back, and David will be leading it. It's a great tour, and it goes right into the keynote, which is presented by Bob Webster. Professor Robert Webster is a professor here, and EPEC is standing at the back. Okay. Yes, he's waving at the back. He is an excellent researcher and one of my favorite roboticists, and he'll be speaking at 1 p.m. So if you want to see the robots beforehand, please go on the VICE tour. And also, finally, if we could be prompt to lunch at noon. Previously, they got a little upset at us for going a little early, so just go at noon and come back for a wonderful talk. I think that was, come back at 1 for a wonderful talk. I think that's all the announcements. So with that, coffee and posters. Thank you. That's my fault. I'm assuming it's your student there. There is one. Okay. So either I didn't receive it, or it could also have just been lost in the chaos of. Yeah. Okay. Thank you for trying.
I missed your posting, but yeah, but like there were so many postings, I just couldn't find it. But question on the
Oh, that works too. There we go.
Should stick them in this invited talks. Nah, I probably should put it on my computer. Just desktop. Look at the USB stick. It's a little slow for active reading.
All videos.
Oh, it's huge.
Oh yeah.
It's all videos.
I mean, some of the talks are like.
Yeah.
I work on math.
Yeah.
And my
Yeah.
friends work on
History equations.
Yeah.
No. I don't think there's maybe 0 equations. Maybe 1. That's the goal. Especially because the math I do is different. wish he was here, our honorary. He's in plenty of the videos. It's his hands, him driving the robot. No, that's great. Pretend we planned it that way from the very beginning, which we did, and then we went to Duke, and then we went back, so it's kind of full circle. Yeah? Oh, okay, all right. Nice. Nice. You got to be adaptable. that student didn't come up to you.
do I just start, or is there anything that? I am not total. All right, welcome back, everyone. So we're going to be starting our third, last keynote, last but not least. It's my great pleasure to introduce Dr. Bob Webster, who's a professor of mechanical engineering here at Vanderbilt. He's the PI of the Medical Engineering and Discovery Lab, and if those of you who have been doing WISE tours, you have seen a lot of his students do demos. And in fact, Dr. Webster is one of the co-founders of WISE, which I believe is one of his proud accomplishments. And I will also say that he has 11 of his past trainees who are now in faculty positions. So he's, among other things, being a great top scientist and researcher, he's also a really great colleague and mentor to not just us personally, but also to many other people. So, and as you will see, he's a very engaging communicator, so I'm excited to introduce Bob. So, please.
Well, thanks very much. It's an honor to be here and speak to you today and tell you a little bit about my experience with startups and how we can get some of this work that we're all doing, that's such great work, into the real world through them. That's the point of today. So disclosures, I better have some if I'm talking about startups. So I've got 2 startups that have come from my lab, both of which I'll tell you about today, and then there's a variety of patents to all these technologies as well. Okay, so I want to start with this question. So how many people here have ever cleaned out an academic lab? So I've done this a few times. It's an interesting experience for those of you who've done it. We did it recently in Olin Hall, which is right over there. It's the big concrete building. This is not my lab. This is the lab of a colleague. I've done it with my lab a couple of times when we moved to different spaces, when we moved into WISE. And it's amazing to do whether you're the PI of the lab or not, right? Because it's almost like archaeological layers, right? You're going down and you're looking at different time points, and you go through these shelves over here, and you see like, somebody's PhD that was a couple of years ago, and you remember it, and you're like, oh, that was such good work. That was really cool. And then you start thinking, especially if you're the PI of the lab, you're like, I should follow up on that. That was really promising. Like, why didn't we go? How did I get distracted with all these other things? And so you get this collection, and the people come back to your mind, and the projects come back to your mind, and you realize, even in just one room, how many cool projects and technologies we have. And then you multiply that by hundreds at a university like Vanderbilt and thousands at all of your universities, and we have so much stuff. So anyway, this is the lab we cleaned out. It looked like that when we started. This is the hallway outside my office when we pulled half the stuff out into the lab to get access to it. You can barely walk up and down there. And here's before and after. So we ended up taking a whole bunch of stuff out of there. But really, the amazing thing to me was the before picture of just like what all we have at universities. So the question, how many great ideas end up like this? They end up just on the shelf. I mean, I look in my office and we have these PhD dissertations of those people who are now out and doing great things in faculty positions. They're sitting on my shelf. Some of those ideas are out there, many are not. So how many great ideas end up like this, and why? And what can we do about it? And what should we do about it? Should we feel this grave sense of responsibility that we're failing because we don't? Or how should we even feel about this? So for me, it's always been a little bit of a source of frustration because there's a gap between what we get out and what we have. And I would argue we should, absolutely not all of us should be doing this, but we should be doing it a little bit more frequently than we are, hopefully, so that we can really get that impact of the things we create. But we'll talk about all these questions throughout the talk. What I mostly want to focus on today is this robot, which I've been working on now for 20 years, since grad school. This is a very, very tiny robot, so it's a millimeter thick, right? Think about a toothpick. It's about that size at the tip there. And it's made from concentric tubes of this metal nitinol, which is what they make cardiac stents out of. So it's highly elastic, right? You can pack it down into a catheter, it pops out and holds the vessel open. We've got 3 different tubes. So 3 different tubes that are inside of one another. If you disassembled them, each one would have a curved tip on it. And the idea is if you put these all inside one another and you twist them at the back end, those curved parts interact and make each other bend. So they're bending and twisting in this interesting way. You get this whole collection of 3 of them, you telescope them in and out, you twist them on the back end, and you get this thing it's the size really of a needle, but yet it can elongate and bend in a way that's conceptually like a tentacle. So as you would imagine, we can probably do a lot of things with this in medicine. At least that was my intuition when I started. I didn't know what, but I thought, hey, I bet we can apply that in a lot of different ways. And the thing that really differentiates it in the surgical robotics world is the size. So it's about 10 times smaller than a standard Da Vinci tool. This is, the robot that's on the market everywhere that many of you, I'm sure, know about. So a little bit of a spoiler. I'm going to fast forward about 15 years, and we've created a robot that looks something like this, which we're now commercializing through Virtuoso Surgical. So this robot is less than half the diameter of a dime, and we can deliver 2 little manipulators through it, and we can help the surgeon aim tools, retraction, lasers, cautery tools, and do surgery in really small spaces all over the body. And so we're going to build up to this, but I'm going to start back with when we just had something that looked like this, and we didn't know what to do with it. And even I'm going to start a little bit earlier than that. So by the way, the diameter is 8.6 millimeter for the scope, 1 millimeter diameter for the tools. And this company is going well. I'll talk more about it later, but we're on the cusp of doing first in human now, raised 16 million. Okay, so where did this all start? So commercial surgical robots today are dominated by the Da Vinci robot. This is the intuitive surgical Da Vinci that many of you, I'm sure, have seen or at least heard about. And the way that robot works is the doctor sits at a console, puts his head in this thing, looks in. This is what the doctor sees with his or her eyes. Your hands are moving like this, and you see these robot hands doing surgery inside the patient. So you can tie really tiny little sutures on blood vessels. That's what's being done here. And the great thing about this robot is it makes laparoscopic surgery way easier, right? Laparoscopic surgery, much better for patients. We don't have to cut them open with big incisions. We just put tools in through ports. This is what it looks like. You can see it would be very difficult. Imagine yourself putting your hand there and trying to control the tool that's down here inside the body very dexterously. Not easy to do, right? So that's the beauty of the robot, is it makes something that's better for patients, easy for doctors to do. Okay, this is what the robot looked like back in 2002 when I started working in this field. Not a whole lot different, really. Obviously, some nice cosmetic differences. They've obviously done a good job with making it simpler, more robust. The setup arms are much more accurate now. But conceptually, it's still doing the same job. And shortly after this robot came on the market, this is again back in the early 2000s, doctors will take anything that you give them, and they'll find lots of cool new ways to use it. And this is an example. So this is a doctor who took all of these big Da Vinci arms that were made for the abdomen and stuffed them in somebody's mouth. So this is a patient's mouth with a whole bunch of tools in there. You can see the cheek is like bulging out to the side. Obviously, this robot was not designed to do this job. Surgeons managed to do it somehow with a robot that was very not designed to do the job. So when I was in grad school, I was looking around at this, and so was my colleague. This is Nabil Saman. He's also a robotics faculty member here at Vanderbilt with me in the mechanical engineering department, also a core faculty member in Vice. He, during his postdoc work, had been building this robot that you see here. So this robot has 4 millimeter diameter arms, so they're a lot smaller than the Da Vinci's are 8, so he'd gone half the size of the commercial surgical robots. And he did that with there's little, inside of it, little mechanisms, right? There's these support discs, and there's these little tubes that you push and pull antagonistically, and that makes it bend. So he'd been able, through those mechanisms, to go to half the size, and his goal was to do a better job of this, like to be able to put this robot in the patient's mouth and not have to stretch and pull on all of the tissues. Super cool robot. This was in the very early stages on the drawing board. He'd published 1 or 2 papers on it. It didn't look this good at the time. And since then, this has been commercialized, this concept, not directly this robot, but the concept has been commercialized by Intuitive. They've built this, the Da Vinci SP robot. So this is 25 millimeters in diameter. Okay, so they're even going a little bit bigger now, right? And it's a cool robot, right? Multiple arms through a single port. Still requires a good bit of space inside the body to work. And you've got that 1-inch, 25 millimeter diameter opening that you need. So my question in grad school was, what's next after the throat? What should we do next? If this is the state of the art, this is what Nabil's working on for his postdoc, like, what should I do for my PhD? And I was inspired by Arnold Schwarzenegger. The next smallest opening, that's right there, is the nose. So maybe we could build a robot that would make this a little easier, better, less painful for Arnold. That's from Total Recall, by the way. So came to Vanderbilt, and I started looking in the operating rooms, and this is video we took really early on when I got to Vanderbilt of surgeons doing this same kind of surgery through the nose. So they're doing skull-based surgery. They can reach all kinds of places on the bottom of the skull through the nose, putting a camera in, and then 2 surgical instruments all in, and they were going through a single nostril here at Vanderbilt. Some other surgeons go through 2 nostrils, but they like the single nostril technique. So imagine trying to put 3 instruments in through a nostril. How much space do you really have there? Not enough. I mean, Nabil's robot was 15 millimeters. The Da Vinci SP is 25. I mean, you can't get something that big into a nostril. So I was thinking to myself, okay, so where do they want to go? They're doing surgery really at the middle of the head. So this is the pituitary gland is a target they go after a lot, and they would love to get up in here to the bottom of the brain to get some tumors out rather than having to do craniotomies and cut through or retract the brain tissue up here. They want to go through the nose to get to all those sites. So pituitary was the one that they were doing in that video I showed you in the last slide. So the question is, how do we get a tool that's this big? Like you could, if you stretch the nostril, you might be able to get 1 Da Vinci tool in a nostril, maybe. You still wouldn't have space for this big wrist to move around in there, right? So my challenge in grad school is how do I shrink that thing down small enough to get it in there? So here's Nabil's. It's, like I said, the tools are half the size, so 4 millimeters. But in sinus surgery, when they're doing that skull-based surgery I showed you, their tools are 1 to 2 millimeters in diameter, and their camera is 3 to 4 millimeters in diameter. So that's how small we've got to get if we want to go in the nose. So I scratched my head a bunch, and I ended up thinking to myself, what is it that makes it hard to make these really, really tiny? The hard thing is the Da Vinci tools have all these little pulleys in here, right? There's little wires that are wrapped around these little pulleys, and you can only make the pulleys so small, or else the wires have to bend through a tighter and tighter and tighter curvature, and wires don't like to do that. They'll fray and break if you bend them through too small of a curvature. Plus, they lose a lot of their force because the diameter gets smaller, and so the lever arm they're acting over gets smaller. So you really can't miniaturize this device much beyond what it is. Even when Intuitive tries to build 5 millimeter tools, which they do and they've released on the market, they use different mechanisms that are more like endoscopes. They have lots of little hinges and pull wires and things like that. So that can get them down to about 5 millimeters. That's the size tools they have on the market. But if we want to go really small, I was just thinking, how do we take all of this mechanical stuff and what is the limit of how far we shrink it? If we get it as small as it could possibly be, is there a way we can mush it into the outer wall of the device? Because any device needs an outer wall, right? So that's kind of the limit. And so that's where I was like, well, maybe if we curved that outer wall and made it elastic, that would let us get the bending actuation that we need into just the outer wall, and that would let us shrink the diameter down small enough to go in the nose. So that was the intuition. And this was one of the first drawings we built of what a system like this would look like here at Vanderbilt when I got here. And the idea was a Da Vinci-like concept. We've got a surgeon at a surgeon console, and then we've got the patient on the bed with the robot delivering tools up the nose. So that was the idea. And then this is what we started building. So a robot that looks really similar to that. It has a few different pieces. So there's the actuation system. This is all the motors and stuff that drive the tubes. There's the manipulators, those curved tubes themselves. There's the end effectors, which actually touch the patient, the surgeon interface, and then sensing, guidance, imaging. So there's all these pieces that interact in a surgical robot system like this. So I'll just give you like one slide on each of these. So the actuation system, we had to solve a lot of problems. One was, how do you sterilize it? So we developed a way to bag all of the electronics and motors and just put the tools in the surgical field, very analogous to what Da Vinci does. We also developed interchangeable cartridges so that we could put different tools in and out of the system. Again, very analogous to what Da Vinci does, but it wasn't clear when we started how to do that with these curved tubes. Like, how do you actually make that work? That's a Da Vinci tool, so you can see the same kind of cartridge interface they've got on there. Okay, that's the actuation system. So it took us a couple years. We were working on how do you mechanically do this. The hardest part was the tubes themselves. Think about how those things are bending and twisting each other. How do you even make them? So the first challenge was how to make them. And the way, this is, you buy nitinol straight. It comes to you straight from the factory. Then you have to put it in a jig and heat it. So we took a car battery and hooked it up to both sides. You saw a little bit of smoke. That was our wooden jig burning a little bit. And then it memorizes the shape that you put it in. So that's how we get it to know that curved shape and take on the correct curved shape that we want it to have. Then the hardest thing that we spent the most time on, and this is a couple PhD dissertations worth of work, is modeling how do you know, as a function of the twists on the back end of the tubes and the curvatures of each tube and the length of each tube, how do you know where the tip is in space? And how do you control it? How do you move it If the doctor moves to the right, how do you make it move to the right? Complicated problem because you've got these interacting, bending, and twisting elastic things that all have to be constrained to one another. But we managed to solve it after a lot of work on mathematical modeling. It ends up being a system of differential equations that you can solve in a computer. We also did some design work. We took medical images, we segmented them, which I know many of you are working on and doing much more sophisticated algorithms. We did this by hand. We segmented out the areas we needed to go in the sinuses, and then we designed the tube sets to have the right curvatures to reach those areas. We also took this is a standard hand tool that they would use in sinus surgery. We cut it in half and put a force sensor in there and took this into the OR and collected force data, so we knew how hard we had to push and what directions we had to push. So that's the manipulators. The end effectors, we built a whole host of end effectors. We can take teeny tiny little cameras and we can put them on the tip of these things. We can make little scraping tools, graspers, we can suction, we can irrigate, we can put laser fibers through them, all kinds of things. We can even make tiny little wrists. So like the Da Vinci had that wrist on the end of it that was super useful for the doctors. The way we do that in a small tube like this is we cut little notches into the tip, then we run a single pull wire down the inside, and then we can bend this thing to the side and get really good local dexterity inside the patient. And we can make them really small. This one's less than 0.5 millimeter. Okay, surgeon interface. How does the surgeon control the thing? So we developed teleoperation algorithms, which would let the surgeon remotely operate the robot, and analogous to how you see the Da Vinci working, right? The surgeon's hands are tracked by a set of master inputs, and then the robot inside the patient follows what the surgeon's doing. We also did lots of fun things like this one. This is, if you've ever heard of the Leap motion controller, it's this little box that you could set on your desk and wave your hand over it and it would track your hand motion. So we hooked this up and we used it to teleoperate the robot. Super fun. My students love doing this. We had our surgeon come try it, and he's like, man, my arm gets tired after a while. So we're like, okay, maybe that's not what we're going to take to market with this thing. But it was a super fun to put together in the lab. And then the sensing and guidance. So many of you are familiar with magnetic tracking from when we take image space to patient space in the OR. We did the same thing, Northern Digital magnetic tracking systems. We put a tiny little tracking coil in the tip of the robot, and we can give the surgeon back the standard triplanar view of the preoperative CT when they're working in the sinuses, so they always know where their tooltip is. So we demonstrated that. And then we also can do a really cool thing with this robot is we can do force sensing. Because it's elastic, if it pushes on something, we know where it should be, and we know where it is, right? So there's a delta in that, and we know the stiffness at the tip, so it's like a little spring. So we can infer forces from deflection of the robot. So that's a really neat thing about these robots that you can't do with most robots because they're built to be very rigid and not deform. Ours do deform, so we can actually measure forces with it. So, okay, so finally, after about 6-7 years of work at Vanderbilt, we had come to this final system. I say final system in quotation marks because it's not going to be used on a patient, but it's final in the sense that we've built what we drew, right? We built the robot, we built the teleoperation surgeon console. We even packaged it up into a set of carts that you could push around a hospital, so pretty practical. We've solved what I viewed as the open-ended challenges, the academic challenges, right? The things that I didn't know how to do when I started doing this, right? So at this stage, this thing's ready for commercialization. There's not really any other PhD dissertations you can get out of this system at this stage. We've written all the papers. So I can't really put PhD students to work on this anymore, not and do them justice, right? It's just not, this is the stage it needs to go somewhere else. This is the kind of experiment that we did at about that time point. This is a simulated pituitary tumor. So these things are benign tumors. They're very gelatinous like this. They have this sort of soft consistency. You need to go scrape them out. Since they're benign, you don't have to get all of them. So you just need to get the material out, decompress the optic nerves are in there, and the carotid arteries. And you want to just decompress all of that, take the tissue out. It's slow growing, so once you do this once, it really won't grow back that fast. But you don't want to put that suction tool up in there because the carotid arteries are in there. And if you catch one of them with the suction tool and rip it, that patient may die on the operating table. So that's why they use this very blunt scraping tool to very carefully pull the tissue out. Okay, so at this time point, I mentioned this thing needs to be commercialized now, right? So my picture was that at this stage, I could get a company interested. One of the big med device companies would come and commercialize it. And I had a couple of patents that I'd written on it. And lo and behold, one did come along. And so I was talking to Medtronic right about this time. And they wanted a robot for doing sinus surgery. This was explicitly what they were looking. They were scouring the world, the academic world, the startup company world. Does anybody have a robot for sinus surgery? And I'm like, yes, right here. So started talking to them, got all the way up to the head of their ENT division. And not only is this a super cool robot, exactly what they're looking for, they have their own magnetic tracking systems, which they're already selling to hospitals for sinus surgery. So it pairs really nicely with a lot of other technologies they already have in their portfolio. So I'm thinking this is a match made in heaven. This should be great. So I have a conversation with them, probably 10 people at Medtronic. And at the beginning, I'm telling them all the stuff I just told you about these curved tiny tubes and how they work really great, and they're the size of a needle, and they act like tentacles, and they're loving it. They're just like, this is what we've been looking for. This is amazing. Yes, sinus surgery, this is what we have to go after. About halfway through that conversation, something interesting happens. So some of the people that I'd been talking to get silent. Some of the other people start asking questions, and they're like, okay, well, can you tell me what is the reimbursement code at the hospital for a skull-based surgery procedure? I'm like, I don't know, isn't that what you guys do? You sell products to these. And they're like, well, how much would it cost you to make this as a commercial product? And I'm like, look at this. In principle, you can make all of this stuff dirt cheap. Injection mold it, all the plastic stuff we have coming from all over the place, the toys your kids have, they're all injection molded plastic. You can make that stuff for pennies. And they're like, okay, I guess, probably. And then they're like, okay, what does the FDA think of this? Like, how do you actually get one of these through, regulatory process? And I'm like, again, you are a big multinational company that has gotten thousands of products through this. Like, why are you asking me this question? Guess what? Those were not the answers that they wanted to hear. So all of the excitement and enthusiasm just immediately drained out of the room, and we said, great, maybe we'll catch up later, but it was obvious to both sides nothing was going to happen. Even though it was the perfect company, the perfect match of technology to their portfolio, it was exactly what I'd had in mind. So I sat back after that meeting, and I kind of scratched my head, and I said, well, we can agree that the clinical value's there. They already have tools doing these sinus surgeries. They bought the clinical value. They bought the concept. What about the financial value, manufacturing, regulatory pathway? And then the real one that I ultimately, maybe after thinking about it for 6 months or a year, came to is this last one. Who's the hero and who's the villain of a proposition like this within a big company? So what it turns out is that the executive who has to make this decision, he probably could have bought the patents to this idea from me, say $1 million. If he'd offered me $1 million, I probably would have taken it, right? I mean, think about yourself in that situation. You probably get a couple $100,000 of that in your pocket for a few years of work that you did in the lab. I mean, that sounds like a good deal. Yet, the companies we've seen sell, when you do a startup company and you work on it for 5 or 6 years, they sell for between $1 and $3 billion. So why is it a good deal for a big medical device company to wait and pay $3 billion for something like this rather than getting it here and paying $1 million? The reason is the executive who's going to make that decision is making a big bet on that technology, right? If it fails, so we look at all of the surgical robot startups in the world. Most of them have been on the order of $100 million of R&D costs within companies that start them. You look at Medtronic with the Hugo system. You look at several other examples. They're $50 to $100 million investment and 5 to 7 years of time. So first of all, the executive may not be around to see the payoff for that. Secondly, he's making a really big bet of his R&D dollars on that. And if it doesn't work, he's going to be fired, and he probably won't ever get a job again. So that's a tough proposition for someone to make, even though if they were looking at the long term of their company, it might be the right decision. So they would rather have me de-risk it in a startup company and then buy it for a huge multiple later. Because think about the decision for the executive at that time point. They're the hero. They just brought in this new super cool robot that's going to chart the course for their company for the next 20 years and bring them all this money. That's why they would rather pay the billions than the $1 million up front. And that's why it's difficult sometimes to license these technologies, even when we've taken them as far as we can in the lab. Okay, so I had a choice then. What do I do next? Do I do it myself? What should I do? Okay, so other important things were happening around this time. The biggest one, I got tenure. Big deal. All the academics in the audience, you know this is a big deal because it lets you reset your own internal goals, right? So I could do more entrepreneurship. I didn't have to worry quite so much about the academic goals. Also, I had a different patent that was granted by the patent office. This was on a steerable needle system, which we've ultimately adapted for the lung in my lab, but that's not part of this talk. Point is, I had a patent granted on a different technology and then licensed for $1 million. So great win, right? But then, fast forward a couple years, and the company did nothing at all with it. So they paid us $1 million, but we didn't have the impact on the world that we wanted to have, right, with this technology. So all of these things were happening around the same time and swirling in my head. Also, around that time, I had a student who I was thinking might be the right person to take this forward. So he was working on this technology, great student, one of those all-around stars where, you know, faculty, if you've had this person in your lab, they're like, maybe not number one at any one skill that you value, but they're top 3 in every skill that you value. Well-rounded, good judgment. That's the kind of person you want running your startup. And so I was starting to think maybe this was the guy to run the startup. So this is Duke Carroll. He was the surgeon that I work with, and he's a co-founder of Vice. And we'd been talking about these robots. He's not a sinus surgeon, but he'd been looking at them in the lab and saying, what would really make sense here? And we agreed that we needed a bigger market, we needed to understand the economics per case, and nail down the manufacturing costs, and then have a regulatory plan. And I didn't even know, what does that even mean? What is a regulatory plan for something like this? And then Duke walked into the lab one day, and he said, we should do HOLEP. I'm like, oh, what? What is this? So I'm like, all right, I'm game. Let's learn about this new medical procedure I've never heard about before. So he began to educate me on this, and the target disease is enlarged prostate, which, men in the audience, it's coming for all of us. If you live into your 80s, 90% of us are going to have enlarged prostate. Even younger ages, it strikes a good number of us in our 50s. There's 300,000 surgeries a year in the USA alone for enlarged prostate. Okay, so this is a good market. And Duke educated me, like, the current approach is called TURP, transurethral resection of the prostate. And they take this endoscope with this electrified wire loop on the end, they put it down into the prostate, and they actually pull out chunks of tissue with this little electrified loop. Doesn't sound very fun, but this is the gold standard way to do it. There was a newer way to do it, probably at that time, maybe 8 or 10 years old, called HOLEP, which was what Duke was talking about, which is holmium laser, so there's a laser fiber that goes through that endoscope, and nucleation, which means pulling out a whole chunk of the prostate. So instead of pulling out lots of little pieces, you actually cut along the outside edge of the prostate, you leave the capsule intact, and you take all the tissue out as a chunk. And this is way better for the patient because if you get all of that internal material out, it doesn't regrow. So with TURP, you have to redo these after a couple of years a lot of the time. You also have lots of other things, like you need blood transfusions sometimes. It's a lot of, since you're making so many little cuts. But with HOLEP, with the holmium laser, you actually cauterize while you're cutting right along the edge. The patients don't bleed, and it's a durable procedure that you don't have to have redone. So people want this, right? This is known. So is it better? Yes, it's way better. It's better in every way. Hospitalization time's lower, catheterization's lower, no blood transfusions, essentially zero reoperation rate, and it even costs less to do. So this is an example. You would think this is done all the time. I'm like, isn't this already being done all the time? The answer is no. It's being done 1% of the time. And why is that? Because it's really, really hard for the surgeons to do. This is what it looks like for the surgeon to do it. So can you tell where in the prostate you are? I sure can't. I mean, there's the bladder back there, maybe, but where am I cutting? How deep am I cutting? Like, it's hard to learn how to do this and difficult for the surgeon to do. So only the best of the best experts take the time to learn this. Now, they have waiting lines, 6 months long, they're booked up for future surgeries. Like, patients are seeking them out, so there's demand, but there's not the experts to be able to do it because it's just so hard to take a rigid scope, put it in there by hand, laser fiber that comes out straight, and you got to tilt that whole thing in order to move that laser fiber and try to cut somewhere. Okay, so this is perfect. This is just like Intuitive. When we're doing laparoscopy, we know it's better for the patient, and maybe a robot could make it easier so more doctors can do it. So how should we make that robot look? So this is our inspiration. We're like, well, let's make it fun. Let's give the surgeon an interface that they'll enjoy. And here's what we built. And so we may not be shooting lasers at enemy starships, but we're shooting them at prostate tissue. So, so this is the first prototype we built in the lab at Vanderbilt. And some of you saw an evolved version of this if you went on the Vice tour. We have a robot that's basically, some components of this robot are still in the one that you saw. It looks very much like this. So at this point, it's 2016, and we're now 4 PhD dissertations in. We have mine, which was the basic idea of concentric tube robots. My first PhD student, who's now a tenured faculty member at University of Tennessee, Caleb Rucker, he did the mathematical modeling. Then Hunter Gilbert, who's now a professor at LSU, did the numerical solution, actually got it to run in real time because the models were originally very computationally intensive. And then we have Rich Hendrick, who did the clinical application and the system that you saw. That was his dissertation. So we're 4 dissertations into this project at this stage. And this is where we launch a company. So Virtuoso Surgical is the company that we founded. Founded in 2016. At the time, Rich still had a year left of his PhD work. So this was the perfect time to found a company, by the way, because we didn't have to pay anybody right away, so we're not burning money from day one. There's no burn. So we started submitting grant proposals, SBIR proposals. I'll get to that in a second. But the founding team was the 4 of us here. So we had Duke, who's the surgeon. We had me, who's the faculty member. Rich, who is going to be the day-to-day guy running the company, managing our engineering team. And then this is Mark Pickrell, who's a lawyer. He was a good friend of Duke's. So we actually got a lawyer on our founding team, which we'll come back to that. It's very useful. So that was our founding team. And we started writing SBIR proposals. So if you haven't heard of these are grants that the NIH gives you for entrepreneurship. And they go to the small company, and they can give you a phase 2 grant of this gives you $1.5 million. So our goal was to have one of these to start on day 1 with the company, have one of these in hand, so that when Rich transitioned from being a PhD student to running the company, he could still get a paycheck. So that way we could found the company with essentially no risk to anyone, because there's no opportunity cost if you're getting a paycheck that you would have got at a big company anyway, if that was what he was going to do next. So that was our goal, and we got this funded, and we did execute on that plan. We sat down to draw a picture of what's the robot we want to build at that time, and this is what we drew. So it's conceptually very similar to what you saw earlier. However, now we have very small, simple plastic pieces in our cartridges, which are very cheap to make. We have all our motors packed into this U-shaped thing, and we can drape a bag over that. And then we have an interface here to a holding arm that will support it. The endoscope's out there on the front. So that's the concept. So we drew this picture in CAD. Here's the holding arm. This is how the whole system looks, surgeon console. The idea here is the surgeon would be scrubbed in and right next to the robot. Okay, and then this is the very first prototype that we put together. This is 2018 at Virtuoso. You can see it looks pretty much like what we drew. And you can see how the operator here is going back and forth between moving the little arms and operating the robot. Here we're just in a virtual reality environment because we don't actually have tubes on that thing yet. So that's 2018. Fast forward a couple years, 2020, the system's come a long way. It looks a lot better, headed toward clinical viability. This is what the tip of it looks like. I already showed you this picture. Here's how it operates. So this is a gynecological surgeon who wasn't part of our founding team. We invited her over, and this is the very first time she ever put her hands on the robot. So this is not a highly trained, 50th case. This is a first case. So we put her in this, it's a simulator of tissue. It's actually made from porcine tissue, but it looks exactly like the inside of the uterus. And it has a fibroid there, and so she's trying to cut out this fibroid. And she's holding it down. She's cutting on one side of it. The key thing to notice here is the user interface. So this is a custom user interface that we really scratched our heads hard about for a long time. But what we came up with is a 4-degree of freedom thing where we have 2 pivoting degrees of freedom in and out along the axis, and then we can twist the tooltip. And the cool thing about this is when you sit down at it, you feel like you have a little piece of a rod in your hands, and what you see on the screen is a little piece of a rod tip. And so as you tilt your hands, it's just really your brain immediately connects the two, and it's like, oh, that's how I move that thing around. And so she's about to do something. Think about how she would do this if she didn't have our robot. It would look more like this. So she'd have a scissors through that endoscope, and she'd be trying to get that scissors around the base. The tissue's deforming away from her. She can't hardly cut where she wants to. Here she's got really precise control of what she's doing. And she can do this maneuver where she flips the thing over, retracts it all the way up, and is able to cut on the other side of it which is a maneuver she could never do before without the robot. And she continues and gets this thing out. So again, first time she ever used the robot. Here's Duke, and this is the 50th, 100th time he used the robot. He's demonstrating this is a prostate procedure. So he's taking out, that's that enucleation procedure I talked about. He's taking out a lobe of the prostate up here. And you can see every now and then he'll go over and he'll reposition the robot. So you can actually do what I mentioned. You do some cutting, then you go over, grab the robot, move it around to a new place, and then do some more cutting. So that's how it works. Here's another example. This is a central airway obstruction. So here, the patient has essentially become a sword swallower, had tilted their head back, and we've put a tool in. This is not our robot. This is a manual procedure with an endoscope. And you can see how hard they have to pull on that patient's head and neck with the manual endoscope to get their tool to bear on the outside edge of the trachea. You want to cut around the outside edge of the trachea to get this big tumor out. And they push really hard on the patient. They'll break teeth. They'll hurt the patient's neck. Not good. Here it is with our robot. So this is a cadaver study, by the way. So the cadaver's right back here. Our robot's right there. And you can see nothing's moving. We're not pulling really hard on the head. The surgeon's able to make some nice controlled cuts of the tissue. Okay, so 2022, let's fast forward again. We drew this picture of the go-to-market system. This is the one we're going to actually put in the OR. This is what it was supposed to look like. And then fast forward 1 year to 2023, April, we unveiled this system to our investors. And this is the system that's going to go into the OR. It's looking a lot more like a product now. Here's a video of how it looks. So this is the interchangeable cartridges. You can see how they pop on. I mentioned the draping. We put a bag around it before. Here's what the whole thing looks like. The surgeon console has come a long way, obviously, certainly in terms of industrial design. This is how it operates. You can see how the surgeon's hands map to the tool tips. And if I fast forward just a little bit, you will see, if I can. Oh, I know, I've got to come over. Here we go. Click on here. Yeah. So this is mapping of, you can see exactly how the hands map. So the tilt of the tooltip maps to the tilt of your hand. The in and out maps to the in and out. And then the twist maps to the twist of the tool. So we've got an electrosurgery tool in one hand, and then we've got a wire loop basket that we use for grasping tissue in the other hand. Okay, so the system's come a long way. So the cool thing here is we're not actually competing against the other medical robots because all of them are focused on the abdomen because that's where they have enough space to work. We're focused on everything else. So everywhere you can use a rigid endoscope in the body, you can use our tool beneficially. Our first applications are prostate and bladder that we're going to go after. Here is, just to elaborate on the bladder cancer. So this is a conventional transurethral bladder tumor removal today. Again, they use that electrified wire loop, and you can hardly see what they're doing, right? They're cutting this tumor into lots of little chunks. You can barely see the loop itself, let alone the whole tumor. And here is an example in a cadaver of us doing a similar procedure. So you can see how with two hands you can cut to very prescribed locations in tissue and get exactly the depth you want, which is essential in bladder cancer because you've got to see if the cancer's got into the muscle, because if it did, then you aggressive chemo and everything. And if the tumor didn't get into the muscle, then you just send the patient home and say, come back in 6 months or a year and we'll do another endoscopy. So a huge decision point to know if that cancer's in the muscle, which they can't do when they have the loop and chop it up into lots of little pieces. And then here is our first live animal. So this is a porcine uterus, and we're showing the same kind of ability to cut. You're not seeing bleeding because we're cauterizing while we cut, and we're able, again, to cut a chunk of tissue out of the wall of the pig uterus. And the great thing about it is, surgeons who didn't even found the company with us are able to do amazing things with it and say things like this. This is Lara Harvey. She's another gynecological surgeon here at Vanderbilt. She's like, this is such a leap forward. If I want one of these, I'd be leaving the OR every day at noon. And this is so satisfying, which you love to hear coming out of the mouth of your customer when they're trying out your system. So major milestones we have coming up in the future. So we passed our initial electromagnetic compatibility testing just 2 weeks ago, which was a pretty exciting time for us. We're planning first in human in just about 6 months from now. After that, we'll do 30 total patients is the idea. And that's a confirmatory study where we just have to follow them for 1 month. And all we have to do is make sure that they had no more complications than the standard of care. It is a clinical study. That's what the FDA is demanding now, but it's not one where you have to follow them and make sure they're cured of cancer or anything like that, thankfully. So we're going to do a de novo filing with the FDA in 2024, midway through, and then approval in late 2024 is our goal. And our indication for use will be something like transurethral robotic surgery. And anyone who's interested in these regulatory things, glad to have offline conversations. I won't say anything more about it, but this is where we're going. So you might be wondering, like, it's great, rigid endoscopy is very useful. What about flexible endoscopy? Can you stuff these things through a flexible scope? Can you do surgery in the colon? We had the same question, but the answer is no, you really can't because of the twisting of these tubes and the curved things overlapping. When you twist them, they wind up torsionally, right? So you have to actually twist the bottom a long way further than the tip goes. And they have this effect that you see in the bottom, this snapping effect, when if you've twisted them far enough on the bottom, eventually they'll just snap and release all that energy very quickly, which is not something you want to happen in surgery. So this can be managed in a rigid endoscope because we put stainless steel all the way out to the tip, almost the tip, and then we just have a little short section of nitinol. But in a flexible scope, you can't do that. You would need the flexible section to go all the way through the scope. So this doesn't work. So can we make something that does work in a flexible scope? So this is a concept that Caleb Rucker, who I showed you a few slides ago, came up with. He's like, well, what if we took two of these notched wrists that I mentioned earlier, put them inside of each other, attach the tips together, and then push and pull one relative to the other. So now we're not twisting, we're pushing and pulling instead. The beauty of this is it works great through a flexible scope because you don't have that torsional windup issue, and we can get the same kind of dexterity through a flexible scope. So I in 2017, hired Josh Gafford as a postdoc to work on this, and he had done his PhD on this super complicated robot. This is a pop-up book MEMS structure, if you believe that. It's got lots of little built-in motors and sensors that they make with like almost an electrical circuit fabrication process, and then they pop it up like a kid's pop-up book. Super cool idea, but very complicated and difficult to get to work in reality. So this guy actually made it work in a pig study, which I was amazed by. But then I said, hey, Josh, why don't you come down and we're going to do something way simpler than this and something that I think we can actually make a startup company on. So he came to work with me, and then we co-founded the second company called Endothea to do this flexible endoscopy device. And one of the things we're doing is kidney stones. So sometimes you'll get a scope in there into the kidney, and the stone will be around the corner, and that's what you're seeing here. You just can't quite reach it. This is a sped-up version of a half an hour of the doctor trying to put that kidney stone basket, maybe bounce it off the wall, try to get it around the corner to get the stone he can see, but he just can't quite reach. So we said, well, what if we gave him a tool that would let him bend around that corner? And this is what Josh ended up designing. So it has a bunch of little features on the handle. Notice it's not even a robot, it's a manual hand tool. And it deploys the kidney stone basket, and then it can steer it, and it can be stuffed through a standard kidney stone or ureter scope that goes into the kidney. This is all the parts. Notice here it plugs right into the port on the standard scope, so now the surgeon can hold the standard scope and our tool in two hands and control all the controls. So this is way quicker to get to market, by the way, than a robot. That's one of the advantages. We also can make it a big, complicated robot. This is a two-arm system. We're going to do colon surgery with it and get out larger lesions in the colon that they can't get out today. And that's what this system is for. Here's a couple more videos. This is the first ex vivo porcine study we did. This is about a year ago, where we can cut out a piece of tissue with electrosurgery inside a pig colon. So here's the team at Endothea. We're now up to 7 million. We've raised all from those government grants that I mentioned, which is great because we haven't had to trade any equity yet. We have an off-campus office that we founded in 2020, right during the middle of the pandemic, but we did it anyway. Still going well. They've actually got to first in human with one part of the system, which I can talk about offline. It's not really the central goal of this talk. And we're about a year away from getting that kidney stone thing I showed you into first in human. Okay, so to shift gears a little bit, people ask me, how does this relate to your work as a faculty member, your university work? How does your lab interact with your startups? Is that a beneficial interaction? What does it look like? So it has been for us. So I've been able to still continue to do university research on these topics. And the reason is, I think this is typical actually, because when you put something into a startup, from an academic perspective, it stays sort of frozen in time, right? There's not more papers, there's not more like cool science advancement that you can really write and talk about. But there are things you could do in that direction. And for us at Virtuoso, it's been things like image guidance. So I connected it to CT scanning, and I did suctioning of blood when you have a hemorrhagic stroke in the brain and you need to get that blood out of there. Stick a needle in and vacuum it out with this little concentric tube. I've done stuff like MRI, we're working on this now, MRI-guided ablation for epilepsy. So we can actually take a curved needle, put it into the head with a laser probe on it, and thermally treat the hippocampus to cure epilepsy with this system, and put the patient in the MRI scanner, do thermal imaging at the same time. So again, these are things that the company would not do because it's not in the critical path for their first product, which is going to be purely remotely operated. But there are things that maybe the company would want to do, 5 years from now, once they have a product on the market, a good revenue stream. So my lab at the university can be sort of the long-range R&D wing of the company, so to speak. So we've worked on things like that. We have an R01 on suturing. How do you put in sutures if you want to sew things back together? That's really hard to do, it turns out. The company's just working on cutting things out because that's way easier. That's their first product. We just recently started working on low-field MRI with Will Grissom, who used to be at Vanderbilt. He's now just moved to Case Western. And so we're going to connect this up, and we're going to do image-guided surgery of focal prostate lesions using low-field MRI, registered with preoperative high-field MRI. So that's a cool project that we're about to get funded. And then we have, with Endothea, we have an R01 on this big, complicated robot system. So the company's doing all the simple hand tools, and the university is doing the big, complicated, software-intensive robotic system with 2 arms. Okay, and then another really cool direction that we're going now in the lab is automation. So can you make these robots do stuff on their own rather than being purely remote controlled by the surgeon? So the question I had is, which is better for automation, a Da Vinci-like robot that's big and stiff, or the Virtuoso system? So we've been doing a lot of work with the Da Vinci for a lot of years in my lab doing image guidance. And it turns out surgeons really, really want imaging in their visual field when they're doing surgery in the Da Vinci. So they'll do surgery, and this is all they have today to look at. And they're thinking in their head about the preoperative images that they saw, right? But it turns out that's not enough, and some of them have resorted to this. They print out the preoperative imaging, tape it to the side of the console so that every now and then they can pull their head out of the console, look to the side, look at the images, and then put their head back in. Obviously, we can do better as engineers than this. So what we've been working on for a few years in my lab is giving them image guidance. And what we do is we'll give them this picture-in-picture display. And obviously, you could make this semi-transparent and overlay it. For various technical reasons, which I think are important, we're doing picture-in-picture here. And the way we do this is we actually register the kidney, this is a kidney, to the medical images by getting a point cloud, and the robot lets us do this. So the robot's a digitizer for us. It knows where the tip of its tool is, so if you lightly trace the tool over the surface of the organ, you can grab a cloud of points, and you can register your preoperative images based on that point cloud. So that's what we've been doing, and we've been trying to guide partial nephrectomy, where you've got a tumor and you want to cut just part of the kidney out and leave the rest of the healthy kidney in place. But you can't see subsurface, so that's where the image guidance helps. So it turns out, though, that the Virtuoso system is actually a way better tool for automation research, early automation research, than the Da Vinci, because the Da Vinci doesn't really know where its camera is. So if you grab the camera of the Da Vinci and you pull it side to side, it will move up to about 4 centimeters at full insertion. You insert it all the way down, grab it, and you can move it with your hand and that's because it has a loose tolerance in the port. It has to, because it can't pull on the patient really hard, or else you could tear the patient's skin. So it can move up to 4 centimeters, and anyone who does computer vision here knows that if your camera is moving around in an unpredictable way, it's going to be really hard to process things and connect that back to where your robot arm should go. So the cool thing about the Virtuoso system is our camera and our arms are attached to one another. So we know where they are really well, and we know the relationship of the coordinate frames. So we can do a lot of work with medical imaging, or with the endoscope images, to control our tools and automate different motions. So this is the approach we're taking, and we're just on the very front end. We've just submitted our first proposal on this, working with collaborators. I wish I could elaborate on all of this, because I'm sure this is the part of the talk that has a lot of you really jazzed, because we're using machine learning for all the parts of this. But we haven't really done it yet. We've just kind of set it up. So all I can say is that what we're planning on doing is we're planning on having our sensors, which in this case is the optical images, and we're planning on using a machine learning approach to extract the geometry of the scene. So we want to know what are the contours of the tissue that is in front of us through that. Then we're going to do a demonstration-based learning approach to train a network to learn what the surgeon's doing here. So you can see he's cutting along this arced path here and retracting with the other hand. So we're going to throw a bunch of demonstrations at a neural network, and we're going to have it learn how to do these similar motions. Will not be easy. But through doing this, we think that we can actually automate some of these procedures, and it may be easier to start on this conceptually way more advanced, complicated robot than what the standard robots are that are out there on the market. So this is another future direction we're going in the lab here at Vanderbilt. The other way that all of this entrepreneurship stuff has resonated for me with my faculty job is teaching. So I've brought all these lessons back, and I've created this class here at Vanderbilt, and the class has MBA students, law students, and engineering graduate students in it at the same time. And what I do is I team them up in a team conceptually just like the one that I launched Virtuoso with, where we have a lawyer, we have some business expertise, and then we have technical expertise. And they operate as a little startup company for the whole year. And I have them go think about what a product would look like, and I have them write an SBIR proposal. So if they choose to found a company after the course is over, they can, and they can submit that and hopefully get government money to support it. And I have them put together a pitch deck. So it's a super fun process. It's a lot like if any students in here have been through senior design, it's like senior design, but for business. That's how I describe it to them. And these are all the actual startup companies that have come. I've been teaching it for about 5 years, and we've had 9 so far and about to be 10 actual startup companies come out of it. That's about an average of 1 a year throughout the whole course of this. There were a couple of years prior to that 5-year period where I and another faculty member were teaching 2 different classes that we eventually merged. Neither here nor there. So we've had about 10 total startups out of this. All of these are still in operation except for 2. One of which had a successful exit and one of which merged with another company. So you could call that an unsuccessful finish. But the rest of them are all still running. They've raised a bunch of money. They're bringing their products to market, doing very well. So this model is a good one to import to universities once we learn it as faculty, in my opinion. So I'll just finish up with a little bit of general advice. So first, to the students in the room, just if you're interested in entrepreneurship, if you're thinking, oh, this is so cool, but I don't know where to start, you're not alone. That's where I was when I was a student. That's where my students who are now entrepreneurs were when they were students. Here's the things I think you should do or think about doing in grad school. First of all, don't worry if you don't do anything in grad school. Grad school is really a time about building expertise, writing papers. You need the papers to graduate. Focus on the main thing, which is getting your degree and doing good research. So if you don't do anything in entrepreneurship in grad school, don't stress, even if that's where your heart is. So that's number one. Second is you should go ahead and just submit an invention disclosure to your university and write a patent. Try to. If your university tech transfer office will agree with you that it's a good idea. So try to at least submit the invention disclosure, try to write the patent, because just going through that process, you learn what patents are all about, what goes into them structurally, and what the claims look like, all of that stuff. Great learning experience. So even if for no other reason, just do it as a learning experience. That's what I did. That patent that actually ended up getting licensed for $1 million, that was my practice learning patent in grad school. So the point is, you never know. So I would advise doing it just for the learning. And take any short-term thing your university offers. They offer a 1-week, 2-week entrepreneurship course. Go ahead and take it. It'll get you exposure to these topics. But don't worry about doing them, per se. But do NSF I-Core. If you haven't heard of this program, you look it up. Take a look. It's a 6-week course that you take that NSF offers, and it's great because it gets you out there to do customer discovery, where you actually meet customers and learn about their problems. So it's really good experience for broadening your perspectives out of an academic mindset. Think through how your work would be commercialized. Talk to lots of people. Ask them about various steps in it, and think about, what would I have to do to get it there? But don't actually do it, okay? Because if you do, it's too much of a distraction, and you won't finish your PhD. This is the biggest one that I emphasize to my students in my class all the time. Best first thing versus it can do everything. So in academia, we are taught to, and we must actually, say that all of our technologies can do everything, can solve all the world's problems. If you write a grant proposal, you're like, think about this algorithm that I've written. Yeah, I'm going to give you one case study in this paper, but it can solve 50 different things, and this whole subfield of the world could be revolutionized by. That's how we have to think as academics, right? That's not how you think as a business person. You have to say, great, there are 50 things. What is the best first one that I should do? And that is a really hard switch of mindset I've seen for my students to have. But that's what you have to have. So practice that. And learn how to write grant proposals, because if you can get SBIR money, that's the best way to fund your company. Okay, general advice to pre-tenure faculty, if there's anyone pre-tenure in the audience. Submit patents. So I submitted a bunch of these before I went for tenure, but don't spend much time on them. Try to spend the minimum time, but at least get them out there. Like put your flag in the ground, and don't start a company because it's too big of a drain and it will probably impede you from getting tenure. I'll talk about that more in just a sec. But that's mainly my advice. And then if you're post-tenure, then you can obviously think about doing this. So a few concluding thoughts. So there's so many great ideas in universities, and I would argue that at a minimum, we should get a larger percentage of them out there to the world. It doesn't have to be all of them, but we should some bigger percentages. You've probably seen this yourself. You can think of so many great ideas that just don't end up out there. So I think more of us should think about this a little bit more often. I think licensing should still be our plan A, because if you're in a university, you want to do research. And so if you can get your idea to make a real-world impact through another company, do it. And then be on to the next thing in your lab. There's always something else to do in research. So still licensing plan A whenever you can. If you need to, like if you really want to have impact and you're convinced this thing can have impact, you got to bring together 3 different ingredients, which is the right leader is the biggest one, the right student or postdoc who's going to go be the day-to-day leader of that company. Because if I were to do that job, I would have to leave my faculty position. And I'm assuming you don't want to leave your faculty position and go be the entrepreneur. So you need to find that person. And that's a lot of the time where the problem comes, is finding that person to do it. A lot of us as faculty have great ideas that we think could be companies, but you got to find the person, and then you got to find the right business concept, which we didn't have in Sinus, but we did have with the prostate application. Consider having a doctor and a lawyer as co-founders. This is my perspective of time and effort required. So time, this is when you found your startup. This is as time progresses, and this is the effort required, and these are the various different people. So I'm the engineering professor, right? So my effort was really, really high at the start. I had to get this thing going. I had to find the people. I had to build the team. I had to write the SBIR proposals. I had to really push hard at the beginning. But over time, as the company's gone on, it's become less and less and less effort for me. And that's because the team has grown and taken on more and more of the technical responsibilities. The leader, the day-to-day leader, this is Rich Hendrick, this is the engineer who's going to go run the thing. His effort is to the max all the time, right? I mean, it's his full-time job, so it's always going to be. The surgeon is kind of the reverse. When you found that company, you've already identified the medical need. You don't have a good enough prototype that you can get any sort of reasonable feedback from your surgeon yet. So the surgeon really doesn't have a whole lot to do at the beginning after you founded the company. But as time advances and you get toward planning for things like clinical trials, having key opinion leaders, other surgeons out there that are going to help try your system, use your system, how you're going to sell it, all of those things, the surgeon time ramps up pretty dramatically. And then the lawyer time, I mean, that's semi-constant, but there's peaks and valleys when, various legal things are due. You have a contract that needs to be worked out. You have licensing agreements for patents. You have patents that need to be filed. Whatever it is, lawyers do a ton of things. You don't even know how many things you need from a lawyer. But it's more or less constant with little peaks and valleys. So that's how it goes for all of the people involved. So just keep that in mind and consider, because if you don't have all of these people on your team, the doctor and the lawyer, then who's going to do this work? It needs to get done. Is this guy going to do it? If this person's going to do it, then they can, by definition, do less of the technical advancement that you want them to do, right? Are you going to do it as the faculty member? If you're going to do it, well, gosh, your time's going to be up here, and how are you going to teach your classes and do your research in your lab? Is the surgeon going to do it? Well, I would argue probably you're not going to have your surgeon doing legal work, so I would say no. But somebody's got to do it. I mean, this work is there to be done. So, and if you're not, some faculty try to launch the company without having that good technical lead. So who does this work if you're doing this? How does it work? You can't do it. It's not really compatible to be the leader of the company and have your faculty position at the same time. So anyway, just a little plot I put together of time and effort required for people over time. SBIRs are great because they let us as faculty leverage our grant writing skills, which we're really good at. Should we all do it? Absolutely not. If you look at this and you're like, gosh, I have no desire to do that, don't do it. Keep doing good science. Not all of us should do this. Some of us should. What I would love for us to do, senior faculty in the room, is make this possible for junior faculty. I would argue right now, I'm on the promotion and tenure committee at the university level here at Vanderbilt, so I see lots of dossiers coming in. And the needle has moved and is moving more toward a more general definition of impact for junior faculty. And I think it can and should move further. I think you should be able to, as a junior faculty, if you define your impact being something through a startup, we should have ways of quantifying that work and that impact, and we should count that in tenure decisions. So that's my argument, and I think we've gotten a lot better at Vanderbilt about that in the last couple of years. It's still a big risk for our junior faculty. I hope that needle moves further to where it's not anymore. And obviously, the reason for that is the impact can resonate with and even improve our day jobs, right? It's let me go in all these new directions in research that I probably wouldn't have done. I certainly would not be doing the automation stuff I'm doing now if I hadn't commercialized the Virtuoso robot. So it can certainly resonate in lots of ways. It also lets you keep those really, really good people around that graduate from your lab, give them productive jobs. You get to keep working with them, which is a huge win. So those are some of my thoughts. Just acknowledgements, lots of people. These are all the people that came from my lab that are in faculty positions now, great people. Tons of physicians, couldn't fit them all on the slide. Same with engineering faculty collaborators. And so hopefully this was useful. Thank you all very much.
Thank you, Bob. We have time for some questions.
Great talk. Thank you very much. What should the cap table be for the startup to incentivize everybody appropriately, preferably with specific numbers?
Well, I can tell you that is going to be case by case different for every team, and you got to do it a little bit by feel. Based on what you want is everybody to feel that they have enough stock that they're motivated to do the job you want them to do. So when we founded Virtuoso, what we did is we did a third, and we did 30%, 30%, and 30% for Rich, Duke, and me, who's my engineering student, the doctor, and myself. And we did 10% for the lawyer. So that was how we broke that down. That was probably a little on the generous side, but the only reason we did that is because we already had a personal relationship through Duke with this lawyer. So we had confidence. So it depends on how well you know your team members. And so then when I founded Endothea, what we did is something a little bit more creative, where we had more vesting going on. So I would urge everyone, don't give out all the stock at the beginning. Give out a portion of the stock with a plan for what that person's role is going to be and an evaluation process to see if they've actually grown into that role. So if you envision your doctor, for example, being the medical champion for this product and actually building that advisory board, medical advisory board, conducting the clinical trials, organizing all that stuff for you. Say that person, maybe they thought they were going to do that. Maybe they didn't even understand that was in your head when you started the whole thing. If you give them the stock commensurate with that job at the beginning, and then they decide they don't want to do that job, what do? You're kind of stuck. So I would say give them a chunk of that at the beginning, explain to them what you expect them to do and want them to do, make sure that's what they expect and want to do, and then create some kind of evaluation process where they can earn that stock over time for, say, we get our clinical trial done, you get this much more stock, things of that nature. And that goes for every team member. So and that's what we did in my second startup, is we kept back some portion of stock, and we awarded some at the beginning, and we had vesting schedules for the various people. So you want everybody to be clear on what their role is, motivated, and yet not be locked in, because you have to be flexible with that cap table as time goes on. So that's the best way I've found to do it. But how the exact percentages are case by case. It's what do you have to do to motivate that person or that other person, or and what do you envision for their role and time and effort and all of that.
Hi, thank you for your talk. That was very interesting. So as someone who's a faculty advisor, has a startup himself, I was very curious about your views on if there's a conflict of interest with open sourcing your work, especially for your students. So if one of your students wants to work on something and wants to open source the work, and it happens to be something that could benefit your startup, what are your general views on if there's a conflict of interest between open sourcing your work and having a wider reach there versus using it as proprietary tech for your company?
Yeah, that's excellent, excellent question. So I think the key thing there is to ask what the goals are for everybody concerned, right? So normally the goal in my experience of open sourcing is academic impact. Like you want other people using your stuff, you want citations to your papers, or citations even to your repository, right? You want academic impact, you want to grow your reputation. So perhaps that's the fundamental goal that the student has because they want a faculty position. The faculty member might have that goal too. I mean, it depends on what they want to see out of the work. They may want instead to have the impact of having the thing affect patients, right? Actually getting to patients. And they may view it that open sourcing actually impedes that goal because now it won't get licensed by a big company and made into a product. So there are different types of impact that you can have. And just having really clear discussions with the whole team of what is the impact we're shooting for and how best to do that. And I think as a student, you kind of have to, if there's a difference of opinion and you've had those very frank discussions and you've clearly evaluated the potential impact, because sometimes there's big potential impact in open sourcing, and there's moderate probability of creating a real product, right? So you have to just have lots of conversations about how big is the impact of each one, what are we going for here individually, collectively, where are we at in our careers, what is the payoff for us? And then once you've sorted through all those things, you have to make a decision. And at the end of the day, if you're a student, you kind of have to go with what your advisor wants. They're paying you, and they're, right, if it's different. But you should certainly both talk about it, make sure you both understand it the same way. And a lot of good advisors will sometimes subserviate what they would want to what's best for that student on a given project. And there may even be compromises. We can open source part of it, but not the real secret sauce. So the key is just really open and honest conversations and talking about the impact and talking about each person's career and where they're at and what they need.
Thank you so much.
Yeah, thank you for a very nice talk. I was wondering, this course you described, I found it very interesting. And you said a lot of companies were founded, but you also said, first get your tenure before doing this and don't do it while you do your grad school. There seems to be a bit of a contradiction there. Isn't it different for everybody when you do this?
Yeah. So it depends on a few things, right? So it depends. So each of the PhD students, so when I form these teams, I find a PhD student who wants to be an entrepreneur. And the first thing I do is I go talk to their advisor. And I say, what do you think about them? Do you want them to be an entrepreneur? Are they working with you? What do they need to do for you in the next year? Will this impede that? And I don't let them in the course if their advisor says no. So I screen carefully for those sorts of things. A student who wants to be an entrepreneur and an advisor who's on board with that, it's a great thing for a student to spend time on in the last year of their PhD, right? It's fantastic. So does that make sense?
So it depends, right? And
Yeah. No, it depends. And my general advice for students was, I guess, more for students on the front end, like earlier on in grad school, when you don't have as clear an idea of what you're doing, but you're just excited about entrepreneurship. So there's a lot of students in that boat. Even toward the end, though, I would still have the same advice if your advisor is not wanting to found the company with you or pushing, thinking in similar directions. I would have the same advice, focus on your papers and get them out the door and then be an entrepreneur. But if you're in the lucky situation that your advisor's on board, then go for it.
Okay, thanks.
Yep, good point.
One last question, please.
One last question. Now, Bob, you mentioned raising money through SBIRs. That's probably not sufficient. You may have to raise through other means. Can you maybe elaborate a little bit on that?
Sure, yeah. So the main sources of funding we've had a few. We've done our funding in a lot of different ways. So SBIRs are wonderful, plan A. There's also venture capitalists. There's also angel investors. And so this is another thing that for Virtuoso was really good for us to have a surgeon and a lawyer who had a good network of people. So we got a lot of individual angel investors who wanted to invest because of their networks, just their networks of friends and everything, on the order of $3 to $4 million early on in the company through angels, just through their networks. So that was great. So angels, if you can get them, SBIRs for sure. There's VC funding, and then there's a fourth option, which we've done, which is called Regulation A+. So it's kind of a hybrid between an IPO and a crowdfunding thing that Congress has created specifically for startups. And we can talk about all the details. There's protections on it, but it allows non-accredited investors, these are not rich people, everyday people in the world, to invest in your company, but they can't invest more than 10% of their net worth or their annual income. So it has some constraints on it, so you can't like clean grandma out of her entire nest egg, you know? That's what Congress wanted. But they wanted ways that small companies could raise money. So we've done Regulation A+, and we've raised on the order of 4 to 5 million through Regulation A+ as well. And we've sold preferred shares, we've sold common shares, so we've done it a lot of different ways at Virtuoso. The best way is the SBIR funding because it's completely free money. It's non-dilutive, you don't owe the government any stock. So Endothea, my second company, has been entirely funded on SBIR so far. We've raised about 7 million so far, and we are probably going to be able to get our first products all the way through to first in human with just that government money. It's certainly conceivable also if it's a software-based company. So ours are hardware, which costs more money. So it's not out of the question that you could go all the way on SBIR funding. Very hard. Now VCs are tough. So we've done a lot of pitching to a lot of VCs. You just have to, it's a numbers game. You just have to do volume discussions and pitching, and maybe something will happen. The challenge with VCs is they have a very rigorous set of criteria. So a lot of them cannot invest unless you're post-FDA approval. So I mean, right off the bat, like none of them can invest. So I can't tell you how many conversations with VCs where they didn't say that until the end of the conversation. They're like, oh yeah, our fund's criteria is we can't do it till post-FDA approval. Why didn't you could have told me that in the first sentence and I would have been like, all right, we're not a match. I wish they would just give you their checklist and you could go down it and see if you fit. There's gotta be more efficient ways to match. The other downside of VCs is the deals that you'll get from them are usually not what you're gonna want. You're gonna have to give a lot of stock for not that much money. So we've tried to avoid VC funding if we could. That's been our goal. We may not be able to always do that, especially once we have to manufacture and sell the devices. That requires a lot more capital. So if we haven't sold to a big company by then we'll have to go the VC route. But you want to delay VC funding as long as possible because you're building value and you're building your ability to negotiate a better deal with the VC the longer you can wait before you take their funding. The other big thing to watch out for is control. So the minute you sell 51% of your company to someone, they have complete control. They can dilute, they can instantaneously create 100 times more stock shares and dilute you to zero. That's within their power if they have 51% of the stock. Or they can sell your patents to somebody. That's within their power. So that control of the company is a big thing to watch out for because whoever has that control, in principle, can do whatever they want with the company. So that's something to be careful of.
All right, let's thank the speaker one more time. Thank you. We are about 15 minutes behind schedule, so we'll go right into the oral session. Thank you.
Teaser, right?
No, it's at the end.
Okay.
Yeah, so.
Can I wait for the guy? Or I think he went to the restroom.
Okay. All right, we'll wait for the other session chair, and we're about to start oral session 8. So there are 4 talks, I believe, and then we have a few short teasers, and then we'll move into the final poster session. Right. So we have a short break until the chairs are ready. Thank you.
How do we start this? How do you start this? You pull something? Hello?
Hello.
Okay, it's already on. Hello? Okay. I am Boubacar Ba from the Medical Research Council unit in the Gambia. It's my co-chair.
I'm Bram van Ginneke from Radboud University Medical Center in the Netherlands. And I will kick off with introducing the first speaker of this talk. That is Jumessi Carroll, and we'll be talking about activations for interpretable disease grading.
Hello everyone, welcome to this presentation. Today I am presenting our work on sparse activation for interpretable disease grading. So, interpretability can be defined as the degree to which a human can understand the cause of a decision. Interpretable model can be useful to trust AI model in high-stakes situations such as medicine. They can also be used for bias detection to ensure that the model is learning the right relationship between the input and the output. The explanation can be also used as learning tools and can even help to discover new biomarker. Finally, the explanation can serve as legal consideration to explain algorithmic decisions. To understand why a model made a specific decision, many attribution map methods have been developed, of which attribution maps are probably the most popular one. As given an input image, they provide a local explanation by highlighting where the model look. However, attribution maps mostly provide post hoc explanation since they are built on black box model. In the other hand, we have interpretable by design model, which integrate the explanation into the model architecture. For example, we have linear model, which are by design easy to interpret, but with low complexity. They are not suitable for image classification. On the other hand, we have prototype-based model, which are built on more powerful architecture and ensure the interpretability by learning the prototype-wise similarity between the training dataset and ensure both the local and global explanation. However, depending on the reason for the explanation may look different. For example, attribution map method will provide local explanation by highlighting the relevant part, where prototype-based model will additionally provide similar prototype from the training set. So in this work, we leverage the advantage of linear model to build an inherently interpretable heat map based model for image classification. So despite the great successes of attribution map for natural images, they have proved to perform, to have a lot of problems for medical field. For example, they are highly variable as they approximate CNN output. In addition, they do not provide actionable insight as they often provide coarse-grained evidence even for very small lesions. In addition, they are not correctly or inherently interpretable since they don't correctly reflect the decision-making mechanism. Finally, they are poorly reproducible with poor lesion localization performance. So, to overcome this limitation, we propose an inherently interpretable model that combines the feature extraction capability of deep neural network with the advantage of sparse linear model in interpretability. In our architecture, the input is first encoded by the BACnet model, which is a modified ResNet version with also a patch-based model with a small receptive field. So this model leads to a feature map of size n by d. Now, from this point, we modify the BACnet architecture by replacing the pooling layer and the fully connected layer by C1 cross 1 convolution. This reduces the feature map, the number of channels in the feature map from D to C, where C is the number of classes. Now, from this feature map, each value inside denote the local evidence or the logic obtained from a small patches of the input. Now, the prediction is directly obtained from a simple average pooling of every value within each feature map. And importantly, the feature map here is directly used as class activation map without any further post hoc explanation. Importantly, the loss function here is regularized using the L1 norm, where, the loss function is regularized using the L1 norm, where the hyperparameter lambda enforces the sparsity. Note that in this model, we regularize the heat map, not the loss function, not on the model parameter, as is usually the case, but on the class evidence map to enforce the sparsity. Now, this hyperparameter lambda denote the sparsity strength and control the trade-off between the explanation and the classification. Additionally, from the heat map, the region corresponding to the relevant path can be easily extracted and present for the clinician for further analysis. By this, our model is inherently interpretable by design, since the explanation is directly used to compute the prediction, and also we integrate the explanation into the loss function. So, to evaluate our model, we use the diabetic retinopathy detection, which is a microvascular complication of diabetes depicted by the presence of retinal lesion inside the retina. It is the leading cause of blindness in the working age population and affects 1/3 of diabetes patients. Diagnosing and grading this disease is based on retinal fundus images, where early diagnosis and treatment can slow down the progression and avoid the patient from vision loss. That is why diabetes patients are recommended to monitor regularly their eye condition. So we evaluate our model on the largest publicly available data set for diabetic retinopathy detection, consisting of diabetic retinopathy grade from 0 to 4, where 4 is the more severe grade. Now, for the first experiment, we evaluate our model for the binary referable diabetic retinopathy detection. We compare it with a state-of-the-art model, since diabetic retinopathy have been extensively studied in the literature. And the classification results show that our model performs comparably to the state-of-the-art model. Here, note that the sparse model is the BACnet model obtained with a suitable regularization value, where the dense model is obtained without regularization. Now, we qualitatively evaluate our method, and the results show that the sparse BACnet provides a more useful explanation, showing that the decision was formed from a small subset of region, a small subset of salient region, highlighted by both the dense BACnet and the GradCam on the ResNet. Furthermore, we quantitatively evaluate our explanation by defining a new metric which evaluates how local evidence contributes to the global prediction. So for this, we compute the proportion of positive and negative activation from respectively non-healthy and healthy images. And the result was aligned with the qualitative evaluation, where here we can realize, for example, that for the sparse model on healthy images, we almost have no positive evidence with the sparse heat map, where with the dense heat map and the ResNet, we still have some positive activation. This is explained by this high value here on local to global metrics. Now, we additionally evaluate the localization property of our model by verifying if the heat map provided by our model was clinically relevant to detect retinal lesion. So for that, we use additional data set of 15 images annotated by our clinician, and the aim was to compute the precision of highlighted region. So given an highlighted region, we wanted to verify if this region really contained annotated region from our clinician. And we found that the sparse backnet, that the region highlighted with, from the sparse backnet contain annotated lesion with high precision, as we can see here. For the second experiment, we train our model for the multi-class tags and again compare it with a state-of-the-art model. We also noticed that our model provide comparable performance to the state-of-the-art ResNet model. But from the confusion matrix, we noticed that our model failed to detect the grade 3 and grade 4 and always tend to classify them as grade 2. Our model additionally provide a class-wise activation map. So for example, this is a fundus image of grade 2, and here we have the probability distribution. Just down here we have the heat map provided by our model. So here we can notice that for grade 4, there is no evidence of positive activation on the heat map, showing that there is no suspicious region corresponding to this grade. While, for example, for grade 2, which is moderate, here we can see very localized region showing some evidence of moderate lesion. Here we can observe some positive activation on grade 1. This is just because grade 2 is an advanced stage of grade 1. So on grade 2, we can still have some lesion corresponding to grade 1. So in this project, we modify the backnet architecture, leading to an inherently interpretable attribution map for image classification. We propose and use quantitative metrics to assess the interpretability. We found that enforcing sparse heat map improved the interpretability, and our model is suitable for classification tags where the region of interest is very small compared to the image size and distributed over the image. We show that our model provides comparable results to state-of-the-art performance for diabetic retinopathy detection, despite being interpretable, showing that we can build interpretable model which preserve the classification performance. So, for the precision evaluation, we send back, here we can realize that our model highlights some region that was not annotated by our clinician. So we send back these patches to our clinician, and most of the time, she finds some diabetes-related lesion inside. So she also stated that our model provides very useful explanation, and currently, we are trying to evaluate the utility of our model in a clinical study. Mainly, one question we want to ask or to answer is to know if highlighting suspicious region, suspicious area of the image can improve diagnostic performance or improve the clinician confidence. So I would like to thank all my collaborators and all those who contribute to this project. If you want to know more about my project, you can reach me for the project session. The code and the paper are also publicly available. Thank you.
Thank you very much. We have time for one question.
Hello, thank you. Very pleased to see some retinal images. Thank you very much. Would you mind going back to the slide that had the heat maps split by the different classes? Yeah, perfect. Thank you. So in the bottom left, you have the healthy class, and you've got your blue spots, presumably because they are negative, because there's a lesion there. There are a couple of bright spots on the optic disc to the nasal side, Do you have any explanation for why that might be? And also, why is that heat map not all completely red? Because if the majority of the retina is healthy, I would expect to see a lot of activation in those regions. Thank you.
Okay, thank you for your question. I don't understand very well. So your concern is about the heat map generated from the healthy case?
Lower down, yeah, the one
okay.
below, yeah.
This one?
Yeah.
Okay, we have not really investigated this because our concern is mainly on the other 3 or 4 possible classes. So because the diagnosis is really based on these cases. So that is why we really need to pay attention. So for example, if we say that there is an evidence here, we really have to check if this region really contain lesion or not. And also, this case is also very useful for the binary task where the heat map for example, grade 1 is empty. So the focus is not on the heat map of healthy case, but the heat map of maybe disease for binary task or one of these grades for the multi-class task.
Okay, thank you very much.
Okay, thank you.
Okay, let's move to the next speaker. Thank you very much.
Okay, thank you.
Okay, our next speaker, I assume is Melanie.
Yes.
She's going to talk about simple and efficient confidence score for grading whole slide images. Go ahead.
Yes. So, hello everyone. I'm Mélanie Luano. I'm a third-year PhD student at École des Mines in Paris. And today I will present you a work that we did to measure the confidence of deep learning models for grading whole slide images. And so the idea was to come up with a comprehensive assistive tool to be used in clinical practice by pathologists. Yep. So just first a little bit of context. So in this work, we focus on laryngeal precancerous and cancerous lesions. And in particular, we worked on whole slide images. So you've seen some of them in previous presentations. And these whole slide images, they are, yes, digital images that pathologists use to perform cancer diagnosis. And so now I just wanted to maybe play a little game since it's the last session of the conference. So can you tell from these images where is a dog and where is a bagel? So I guess we all agree that the dog is on the left and the bagel is on the right, I hope. And I think we can agree with a quite strong confidence. But what about this image? I think it's a little bit more trickier, and maybe we are not as confident as for the previous images. And so I add another example because it was fun. So where is the dog and where is the mop? So again, I think we can all agree that the dog is there and the mop is there. But what about this one? And so, yes, this kind of ambiguity in the data is very common in histopathology images. And there are actually very few tools that exist and that actually are applied to histopathology to measure the data ambiguity. So now if you go back to laryngeal lesions and to histopathology, so you see that laryngeal tissue can be affected by precancerous patterns and cancerous patterns. And this pattern that can be a different degree of severity, and the severity is correlated, of course, to the risk of developing a cancer. And so in the larynx, laryngeal areas, the abnormalities are ranked into 4 categories. So normal tissue, low-grade lesion, high-grade lesion, or carcinoma. And you can actually see from the sketch that the lesions, they are sort of present on a continuous spectrum of lesions, which makes the borders between each classes
kind of blurry, subject to noise, and subject to the pathologist's subjectivity. So if we can make the parallel with the previous example, so there are cases that might be very easy for pathologists to classify, but some cases that are on the border of the two classes and that might be more trickier to classify and to perform diagnosis on. So that's why there is a real need, at least for this use case, but for many other use cases, for a companion diagnostics tool for AI models to really help the pathologists gain in standardization and in reproducibility. So with that in mind, we decided to develop this comprehensive companion diagnostic tool. So we first developed an AI model for grading wall-size images using weak supervision. So this was published in another paper. And as I said, we developed and we validate a confidence score that we benchmarked against other popular uncertainty estimation methods, and that I will show you later. What I also wanted to show you, it's some recent work that we did where we actually took this comprehensive assistive tool and we gave it to pathologists, and we were able to measure if the tool was actually helping them in their routine practice. And I will show some results about that. So now about deep learning models confidence. As I said, there are some existing methods, Monte Carlo dropout, deep ensemble, for instance. They are quite popular, but they have one major drawback. It's that they are very computationally expensive, and this is a huge problem for histopathological data sets that are usually very big and that contains a lot of tiles, a lot of patches. And also, they are not designed to be grade sensitive. And I showed you that this grading task is a bit more trickier than just a standard classification task. So that's why we proposed a new confidence score that is actually grade sensitive, that is also simple and intuitive, as you will see. It does not need extra trainings or inferences. It does not need extra architecture changes. It's easily interpretable. And also it mimics the pathologist's behaviors, how pathologists are reading the slides. And I will explain why. So about the confidence score, so it relies on a first step. And the first step is actually training the network with a grade sensitive loss. So this loss came from another paper that I cite below. And so this is a loss. And so basically what does this loss, it takes into account the fact that the classes are ordered. So it's a sort of regression on this cost matrix, and this cost matrix is defined beforehand by experts. It's kind of arbitrary. It depends on the medical task. Basically it's penalized more larger errors and less smaller errors. So for instance, if the model is predicting a class 3 instead of a class 0, it has a higher cost than if it predicts a class 1 instead of class 0. So the output of this network, this loss, is a vector of costs. And from this vector cost, we can compute our confidence score. And so, sorry, it's maybe not aligned. But basically, what we do to compute the confidence score, it's take the network outputs, standardize it a bit. So we just invert it and take the softmax. So our confidence score fits between 0 and 1. And then what we do is really reproduce what the pathologist would do when he would perform a grading. It means that the pathologist will hesitate between two classes, two adjacent classes, and our confidence score is defined as being the difference between the two most probable classes. And we show in the paper and yes, in our benchmark that this quantity, this difference, is actually correlated with the model's hesitations. So now if we just take a step back and if we get a bit the big picture. So here it's an overview of the overall pipeline that we developed. So the input of the model is a wall slide image. We train a multiple instance learning model with weak supervised labels, and we train it with this cost-sensitive loss. And so the output of the model, it's the classification, so one of the 4 grades, and also a confidence estimation. And we also dichotomize the confidence scores between two categories, low confidence and high confidence, according to a particular threshold that we can optimize depending on the use case. And so actually, when we separate the slides between low confidence slides and high confidence slides according to this threshold, so here we choose the median, we see that the confidence score is really managing to separate the slides that are more misclassified or poorly classified compared to the other slides, as you can see in the difference in terms of classification performance. And what is also interesting from these confusion matrices is to see that most of the low confidence slides are actually the slides that are low grade or high grade, and it's known for pathologies that these classes are very much more difficult to grade. And the easiest classes are the class 3, so carcinoma and normal class. So it in a sense shows that the confidence score is again mimicking the pathologist's behavior. And targeting the cases that are actually more ambiguous for the pathologist. And so we can link back to the example. And so one other experiment that we did was to ask two pathologists to review the same set of slides, and we measured the confidence score on the slide on which they agreed on directly and the slide on which they disagreed. And on the slide they disagreed, it means that the grading was more trickier and maybe more ambiguous. And you see that the confidence score is lower when on the slide they disagreed than on the slide they agreed. So again, the confidence score is matching with the cases that are actually ambiguous for the pathologist. And so now, does this pipeline AI assistive tool is really helpful for pathologists, as it really improves the reproducibility. So we did this study where we actually asked a pool of 8 pathologists to review a set of slides with the AI assistants and without the AI assistants. And we compared their diagnosis with the consensus labels that we defined beforehand. There were a washout period between the two reviews, of course. And so here are the results. So we were very happy because we didn't work for nothing. So here you can see the linear kappa, which is a measure of the reproducibility. And here are the reproducibility measure for each of our subgroups of pathologists with the AI assistants and without the AI assistants. And we see that for non-experts, for junior, so residents, it's like junior pathologists, and non-head and neck specialists, they reach the same level as expert specialists thanks to the AI assistants. And I don't show it, but also they gain much more, they gain in reproducibility because their diagnosis is much more standardized. And so the last result that I wanted to show was this. So we tried to assess if the confidence score was actually guiding the pathologist and how the confidence score was used by the pathologist during the diagnosis. So here you can see again the reproducibility, so the linear kappa, for the slides that were tagged as having a low confidence prediction or a high confidence prediction. And we see that for the slides that were tagged as having a low confidence prediction, so there were maybe more difficult slides, but you see that there is no much difference between, in terms of reproducibility, between the non-assisted and assisted review. So probably that the pathologists, they didn't really took into account this, the model predictions when it was tagged as having a low confidence, whereas you can see there is a difference for the slides that were tagged as having a high confidence. So to conclude, we defined a confidence score that is very specific for the grading task. And as I told you, the grading task is a quite difficult task because of this ambiguity in the data. And we showed, so in the paper, that our method is better and also less computationally expensive than other methods that I mentioned. So you can see the benchmark actually in the article. You can also come to the poster if you have more questions. And I'll also show you some results about the assessment of is really AI assistants useful in clinical practice, at least for this particular use case. And we show that non-experts, junior and non-head and neck specialists, they reach the same performance as experts thanks to the assistive tool. So we hope we are moving towards more assistive tool in routine, and yes, this is a small proof that that can actually be useful. Thank you very much. I thank all my co-authors, my supervisors, and I hope you have questions.
Thank you very much. Do you have any questions?
Hi, yeah, nice talk. So I had 3 small questions. I'll just go, you can stop me if it's too much.
Sure, yeah, well,
yeah,
we don't want to
cool.
do 3.
So first was when you compare assisted, non-assisted, and you showed 3 different panels of experience for the readers, like how many readers were in each of these pools?
At least 2, and I think we had 3 specialists and 2 residents. Yeah, so 8 pathologists in total, but at least 2. So I also have the result, like global result, and they are showing the same trend. Yeah.
Okay. Another thing was when it came to the assisted reading, were they made like both the AI reading and just the image itself? Were they made available at the same time, or were these readers allowed to make their own opinion and then the AI result was provided, or you know?
So they had access to the AI output, the AI assistants at the same time as they were viewing the slide. So they view the slide, they had the prediction, they had the confidence score, and they also had the heat map, the attention heat maps, to help localize in relevant areas according to the model.
Okay, and yeah, the last thing.
You want to give somebody a chance? Please, you can talk to offline,
right, cool,
please.
Cool.
Yes.
All right, we'll catch you
Let's
in the
have
poster.
any other person ask a question. Yeah.
Thanks for the talk. It was great. I just wanted to ask and pin down a bit more on this one. So I just wanted to clarify, did you measure how, whether or not the model is biasing, for example, the junior people who are reviewing this? You know, because they agree better when they have the AI model assistance, but is that just because they're conforming to, they have less experience and they're conforming towards the AI model's prediction, whereas the specialists don't do that? Are they conforming to the correct assessment or just to each other?
So actually the reproducibility here is, so the diagnosis of each pathologist is compared to a consensus label that was defined by other pathologists that did not participate in this study, that was not in the pool. So it's really the reproducibility with this gold standard label that was not used for training the model. So the model never seen this gold standard label. It was trained on like noisy labels because we only reviewed a small portion of the data set. So I think, yeah, there were not, yeah.
So it's not agreement between them, it's to the gold standard?
Yeah, it's to the gold standard, yeah.
Okay, thank you very much.
And so still the gold standard, you can argue that maybe it's not an absolute gold standard, but we also did a pairwise, we measured the pairwise reproducibility for each of the panel members, and we show that there is also a significant difference between the assisted and assisted review, so yeah.
Thank you.
All right, let's thank the speaker one more time.
Thank you.
All right, so the next talk is Frozen Language Model Helps ECG Zero-Shot Learning, and will be presented, I think, by John Lee.
Yeah, good afternoon, everyone. My name is Jun Lee, and I'm an undergraduate from the Jenny University. It's my honor to stand here because maybe I'm the youngest participant in the MIDL, and I'm a bit nervous here. So yeah, and I'm going to talk about the frozen language model helps the ECG. yeah. Thank you so much. Thank you so much. And I'm going to talk about the frozen language model helps the ECG zero-shot learning. And the electrocardiogram, or ECG, is a diagnostic tool that is widely used in the clinical practice. It can be detect like the myocardial infarction and the atrial fibrillation. And the deep learning models, such as the convolutional neural network and the recurrent neural network, have been shown to be highly accurate in classifying the ECG for a variety of the cardiac conditions. And the supervised learning is the most common way in the ECG deep learning. And supervised learning, however, supervised learning requires a large number of high-quality labels to achieve the strong generalization performance. And in addition, some forms of ECG, such as the ST elevation myocardial infarction, are difficult to detect and require the manual interpretation of the ECG by the trained cardiologist. And nowadays, the self-supervised learning methods have been taken away, and some self-supervised learning methods, such as the Sinclair, have been shown a promising solution. And here, existing ECG self-supervised learning methods still require a large amount of annotated data in order to fine-tune them for the downstream text. And this requirement hinders the application of the ECG method, as some heart diseases are really rare, and this which leads to the problems with the zero-shot learning. Zero-shot learning means that the model does not need any annotated samples for the unseen categories. And this is achieved by the explicitly learning shared features from the visible samples, and then generalizing them to the unseen samples based on the description of the unseen class features. And specifically, this description often draws on the knowledge from the external medical field, such as the textual ECG report. And zero-shot learning in ECG face some challenges, and the first challenge is the semantic gap. That is because the ECG and text are two heterogeneous modalities. ECG is continuous and sparse signal, but text is discrete but has dense information. And the second challenge is the domain adaptation. The self-supervised learning method may be sensitive to the unknown domains, and this makes it difficult to adapt to the new domains. And the third challenges might be the scalability. The zero-shot learning models need to learn a large numbers of representation and apply them to the downstream text, which leads to large computational cost for the model. And here is the method. Currently, there is some work that introduced the multimodal contrastive learning into the self-supervised learning, such as the CLIP. And using the descriptive text as a multimodal signal, the model can be obtained to the self-supervised performance. To take the advantage of the textual ECG report, we propose a novel method called multimodal ECG text self-supervised pre-training, and we call it MAT. And the figure is the framework of the MAT model. MAT model takes the ECG and the corresponding text report as input and feed them into a framework that is a multimodal contrastive learning framework. And the framework contains the language model and an ECG encoder. And the language model here, we use the clinical bird as a language component. And here we freeze the language model, which means we don't train or fine-tune it. We just keep the parameters free. And the ECG encoder, we choose the ResNet 1D18 to be our ECG encoder. That is because it can obtain the representation. And the projector is to align the text and the ECG like a Sinclair projector is a two-layer MLP, and it can let the language model, the embedding of the language model to be the same dimension as the ECG. And finally, we compute the similarity and we can obtain the probabilities. And here is the zero-shot learning classification. A segment of the ECG is used as input. To evaluate the zero-shot learning performance of a model on a multi-label classification text, we extend the discrete labels into the full medical diagnostic statement and feed them into the language model to obtain the embedding representation. And finally, the similarity between the ECG embedding and the text reembedding are computed to obtain the probabilities, which can be used to classify the various categories of the ECG. And here's the experiment section. Here we use the PDB-XL dataset to train the MAT model. The PDB-XL dataset contains clinical 12-lead ECG of 10-second durations, which each ECG segment is paired with a corresponding ECG report, and the labels of the ECG were assigned to the 3 categories: diagnosis, form, and rhythm. And in the current experiment, we focus on investigating the ECG and text pairs without using any other labels. Following the experimental setup for the previous research, we extracted a multi-class classification text, which is the PDB-XL test set. And there are 1,000 samples on each test set. And for testing to evaluate the performance of the pre-trained representation framework for the classifications on the external data set, we produced an MIT BIH test set following the method described above. And to demonstrate the performance of the MAT, our approach is to compare some baseline. And the first baseline is the ResNet 1D18. It's a random initial ResNet 18, and we choose this for showing the performance of the small data fraction fine-tune. And the second baseline, we choose the SimClear. It's a self-supervised contrasted learning model that achieves the good performance in the self-supervised learning. We use the 5% of data for the fine-tuning. And the third, we use a supervised manner. We train the ResNet 1D18 as a supervised manner in order to compare the learning performance of our method with that are fully supervised. And finally is our result. We access the ECG classification using the commonly used metrics like the accuracy, precision, recall, and F1. We first perform a zero-shot classification of the PDB-XL test set for the diagnosis. It can be found that our model outperforms all other self-supervised learning methods. And then we evaluated the PDB-XL test set for the ECG form. It can be found that our method outperforms all other self-supervised learning methods too, with a comparable performance to the supervised learning. And last, we evaluate the transfer learning performance. Here, the table 4, we use the MIT BIH test set. And the table 4 shows the performance of the comparison under the cross-data set testing. In general, MET outperforms other state-of-the-art methods and even outperforms the recall and F1 of the supervised learning. This suggests that the features learned by the MET are robust and have the potential to be generalized to other data sources. And here's our conclusion. Our proposed method, the multiple ECG text self-supervised retraining method, is the first work to apply a large language model for the ECG self-supervised learning. And the prior clinical knowledge from the frozen language model can be fully utilized to assist in the zero-shot ECG classification. And MAT is independent of the annotated categories. Even if the external dataset categories are unseen, the classification can be done directly with a zero-shot, unlike other self-supervised learning which require the fine-tuning. And third, the experiments demonstrate that the MAT can be adapted to any other classification tags without the need to fine-tune on different tasks. And MAT does not require any annotated data, but can exist the supervised and the self-supervised learning methods of fine-tuning with a small scale of the annotated data. Thanks for listening.
Thank you. The paper is open for questions. If not, I have a question. So I think I saw on one of the slides that you did do a 5-class classification because you compared with 5 different text prompts.
You mean the 5% of the the data or
No,
other?
on a previous slide you had 5 different prompts that you can compare to, 5 different texts.
5 different tags. Do you
Yeah,
mean
there,
here?
There. So there are like 5 options down there, right?
It's a classification tags, and we choose the 5 labels and just classify by the ECG encoder. And here we just give the label to the language model, and it can be compared to embedding here like the T1, T2, and the T1, T2 is computed the similarity with the embedding of the ECG, so it can be calculated to obtain the probabilities.
And then what are then the rare conditions you mentioned for which you have few examples? Is that one of these 5 classes, or?
Yeah, we have to do this experiment, but it's my mistake. I haven't put the some case in it. Yeah, there we can find some rare disease to when we used to in the external data set like the MIT-BIH. Yes, and in the MIT-BIH, in this test set, some diagnoses are rare, and we found that it is more powerful than the supervised manner.
Thank you.
Thank you very much.
Okay, we have our final speaker of this session, and I assume it's Yewin Liu, right?
Mingshan Lin. Okay,
Mingshan
at
Lin.
the correspondent.
Okay, good. And he's going to talk to us about an end-to-end framework for diagnosing COVID-19 pneumonia via parallel recursive MLP model and by LSTM correlation.
Okay.
Go ahead.
Good afternoon, everyone. My name is Mingshan Lin. I'm from Weill Cornell Medicine. Today, my presentation is related to the COVID-19 detection based on deep learning. This is outline for my talk. My talk includes 4-part background, methodology, experiment result, and conclusions. First, I will introduce the backgrounds of my research. For the global situation of COVID-19, there are 765 million confirmed cases and 6.9 million death reports. And the WHO has declared an end to COVID-19 as a public health emergency, stressing that it does not mean the disease is no longer a global threat. There are several methods to detect COVID-19. One popular method is nucleic acid detections, but this method has several limitations. First, high false positive is mean healthy people is misclassified as patient with COVID-19. Second is a specific ability to pollutions. Third is low efficiency. And chest CT is another way to detect COVID-19, but this imaging technique also have 2 major limitations. First, exposed to radiations, high cost. And long ultrasound is another imaging technique to detect COVID-19, but this imaging technique also have 2 main limitations. First, low resolution. Second, less intuitive. And the chest X-ray is the first imaging technique to detect COVID-19. This technique has 3 major advantages for COVID-19 detections. First, affordable price. Second, simple operation. First, strong intuitions. But if it's time-consuming to detect COVID-19 based chest X-ray manually, so therefore it's necessary to develop a deep learning method for detecting COVID-19 based on chest X-ray. There are many methods has been proposed to detect COVID-19 based chest X-rays, but most of them have 2 common limitations. First, don't avoid the influence of other tissue in the chest region. Second, they use the total convolution filter number as the as input for the classify. Maybe redundant feature can potentially affect the classification performance. In order to overcome these two limitations, we propose a method to diagnose the COVID-19 based on deep learning. It's an end-to-end classification model, and this model contains two main modules. One module is multi-class learning module for object detection and feature map generalization. The second module is MILP bio-LSTM classification module. In the following slide, I will provide detail for these two modules and highlight our contributions. For the first module is multi-task learning module for object detection and feature map generalization. Based on this name, we can know that this module have two main functions. The first function is object detection. The second one is feature map generalization. For object detections, we want to detect the checks cavities because we want to reduce the influence for other tissue. For the object detection, we mainly based on the fast RCNN. We can see that we use image as input, and we can detect the checks and includes the other tissues. Another one is the feature generalizations. For the feature generalization, the convolution backbone network has 13 convolution layers. Therefore, they can generate 13 feature maps. But in this study, we want to reduce the computational complexities and also want to reduce the redundant feature. So we select 5 of them, 4 of them from the convolution networks. They're the last layer of the recession fields, and the fifth one is the original images. So we can get the 5 dimension features as the input for the classification module. The second module is the classification module, and this module have 2 very important components. The first component is MLP layer. These MLP layers have 3 layers, and the idea to design these layers is mainly original from the transformer, because transformer will use the patch to get the get the correlation between each patch to get the local correlations. So we also separate the image as a small patch and then flatten the patch, then through the convolution to get the correlation among the different patch. I think it can help us to get the local correlation among all these patch and get the local information to improve the classification performance. And after we get the output from the MLP layers, we use it as the input for the bio-LSTM. For LSTM model, we usually apply it for the sequential data. But when I design this model, I think if we have the feature map from different scale, then why I can regard it as the sequential data and apply the bio-LSTM to explore the relations among these different feature maps. Maybe it can help us to improve the performance. So after we get the feature from the bio-LSTM, we put it into the classifier and get the prediction result. And in this study, we use a public data, and this data have 3 classes: normal, COVID-19, and other pneumonia. And for the COVID-19 cases, we only have 183 samples. In order to reduce the unbalanced problems, we expand the COVID-19 sample to 1,464 by random angle rotation. And in this study, we 10-fold cross-validation was used in this study. We repeat this study for 5 times in order to verify the robustness of the proposed method. This is the example for the object detection and feature map generalization. According to this figure, we can see that the feature map is not exactly the same for these three kind of categories. So maybe it's also give out the hint, maybe the feature extracted by our algorithm have potential to detect the COVID-19 among the other disease and then from the normal patient. And the figure A and figure B show the loss curves and accuracy curves when the model training on 5-dimensional feature mapped. And the table 1 show the quantitative elevation result for the proposed methods because we repeat the tenfold validation for 5 times. So we can get the mean value for all these evaluation matrices. We use 5 evaluation matrices in the study: accuracy, precision, specificity, recall, and event score. According to the last column of this table, we can see that all evaluation matrices above 0.98 is mean our method achieve pretty good performance for COVID-19 detection. For table 2, we also want to verify the feasibility of the 5-dimensional feature as input for our model. So we compare the 5 dimension with the 14 dimension as input. 14 dimension compose 13 dimension from the convolution network and the original images. And from this table, we also can see that our 5-dimensional input not only can reduce the computational complexity, but also can improve the classification performance. As I mentioned before, we think the Bayer LSTM can explore the correlation among the feature maps. So we also conduct an experiment to see if the Bio-LSTM can make contribution to the overall performance. And from the table 3, we can see that all the evaluation matrix inputs maybe from 2 to 4% after adding the Bio-LSTM, because they are these 2 models experiment on the same condition, but one without LSTM. In order to verify the effectiveness of our proposed model, we also compare with several state-of-the-art models for COVID-19 detections. And from this table 4, we can see that our model achieved the highest evaluation matrix for among all these methods. I think it's also a way to indicate the proposed method have potential apply for clinical practical. Then we get conclusions. In the study, we propose an end-to-end deep learning framework to achieve rapid and accurate diagnosis of COVID-19. This is an end-to-end. This end-to-end model achieves the task of object detection, feature extraction, classification at the same time. Compared with the multi-state classical data model, it has better operation efficiency and can better meet the clinical needs. Because we use the INLP for detection, so it can realize the position detection of the trace regions. So they can help us to get the more precise feature for the trace regions. First, because we use the different recession field and multi-scale INLP module, so we can achieve the more efficient local and global informations. And the Bio-LSTM module also can help us exchange the information among the different among the feature generated from different channels. It's also another way to improve the classification performance. Last, compared with the advanced state-of-the-art model, our model can achieve a highest performance for all evaluation matrix in the study. Thank you for listening.
Thank you. Any questions? You may go ahead.
Thank you for your talk. I have a clarification question. You had mentioned that you used 10 different rotations for the COVID-19 images.
Yeah.
Did you do this step before or after making your 10-fold consolidation splits?
We did it before the fit that into the model, but we also apply data augmentation technique during the flying training. First, we augment the data. Then we also apply the augmentation technique during the training.
But does it mean that when I have a test set, a test case, that already 9 differently augmented cases of that same original COVID-19 were in the test set?
Yeah.
Okay.
Thank you.
Yes, let's. Okay, you had the same question. Okay, let's have.
A pretty simple question. Thanks for your talk, by the way. You claim that nuclear acid tests you have a lot of false positives. Where does your ground truth come from? Your COVID diagnosis.
Ground truth from this, you mean the augmentation table? Or
No. You said you had 183 COVID positive cases, but how were determined they were COVID positive?
COVID positive.
Yeah, where's the ground truth? Where did it come from?
The table have the data
yeah,
have
but
the.
How did they determine? Okay, well, thanks for your.
Okay.
Okay. Say that again. Go ahead.
So I would suggest that the slide you showed was LFD, which has got a high false positive rate. But typically, ground truth COVID is PCR, which is more accurate, I would say. It may be, but I just.
Okay. Well.
I've almost posted teaser now.
You wanna? Yes. Yeah, let's thank the speaker one more time.
Okay, thank you.
All right. Thanks, everyone. I think this is the last oral session. We have one more teaser, right? Good.
So before we break into coffee and into the last poster session, I have announcements. And of course, I will hold the announcements until after the teaser so that you all stay and listen. But my first announcement I'll give you first is that I accidentally skipped this teaser talk, so my apologies to him. And we should be able to see it, so that would be important too. So this is paper P054, also known as W10.
Hello, everybody. Some of you met me. My name is Nick from Duke University. I'm honored to have received the bonus teaser talk slot. Just real quick, so everyone knows about domain shift and that it's often caused by difference in scanner settings, either between different hospitals or even the same hospital, different scanner model, tons of different settings like field strength, TE, TR, that kind of thing. But the question is, if we're interested in like image-to-image translation for data harmonization, domain adaptation, those kinds of things, maybe those types of methods could be better informed if we understand the relationship between these scanner settings and the image that is generated. So basically, my project was, can we train a model to predict a lot of these acquisition parameters all in a single forward pass from a new breast MRI image? Surprisingly, yes, we could to very high accuracy to a lot of these settings, such as everything from scanner manufacturer and model, field strength, even contrast agent, TE, TR, that kind of thing. And it has some cool applications for, like I said, harmonization, generative modeling of breast MRIs, that kind of thing. So if you're interested, please stop by. Thank you.
Okay. So my announcement is quite short, that we'll be resuming at 4 p.m. I know that we're breaking early, and that will cut the poster session short, but because people have sometimes flights, and also we want the awards to happen before people fly away, we'll be resuming at 4 p.m. Thank you.
Thank you.
going to work because the microphone's in the way. So, okay. We got to make sure the mic's on this side. So the mic's on this side. I get a photo of you shaking their hand with the Vanderbilt logo. Then have them line up here. We're done on this session. Daniel, can you help me move this like a step back?
Yes.
Oh, dude, 1, 2, 3. Oh, it's so buff.
I wanted a picture of that moment there.
This is the light of table. And now you can say, please wait here. And then we can get a photo of all of them with you and Vish.
So all 6 of them, or just 4 of them?
All 6. I would just give everyone who wins the award. We'll have the students come up first. We'll take 4 academic photos, and we'll take all 6.
And just in case one of us probably will be sending a test that way.
Right,
No, but say,
I know.
Vish is going to be with you to award the NVIDIA awards. So, Vish, I need you to not have this in front of your face. So, just move it down. Just make sure it's not like this. No, I would.
So they can just stand up wherever they are.
Just stand up wherever they are, then. But having you and Vish with the awards, and then I will put the actual awards behind you. Why don't we just put the awards on the table? And then I'll go get the review awards and put them on the table right now. If they want a different size, they're exchangeable. Just talk to Tegan or myself.
All right. I have the most fun job of the entire week. So I get to present the awards. And what I'm going to do is I'm going to tell you a little bit about how the program selection process went, and then we're going to get into the awards. So we had 8 program chairs, including myself. We had Mirabella, Shasha, Despina, Jack, Martin, Christian, and Tobias. Unfortunately, nobody except Jack and me, who are local, are here. So, but they have all been very, very active, and we've had countless Zooms and even more emails throughout the process. So I'm very grateful to the entire team. We had 40 area chairs during the full paper track. So I have the names up here. I believe a few of them are in the room. And we had 188 reviewers. So I would like you to please stand up if you review for MIDL 2023 so that we can do a round of applause. Thank you. This is really sort of the most crucial aspect of the entire selection process, right? Because without good quality reviews, we do not have good paper selection process. So as I was putting together this team, I was looking at the numbers, right? So we have 8 program chairs, 40 area chairs, 188 reviewers. And I got a little bit nervous. Is this a pyramid scheme? What have I done? But then as I started looking into, as we get further into the process, it starts to come back around, right? Because the reviewers, they provide their feedback to the area chairs, then the area chairs back to the program chairs. And you start putting in these connections from your earlier thoughts about each paper, right? And this is starting to become very familiar looking. Do you know what this is? Shout it out, please. Yes, it's a UNet. So I was like, all right, I did okay. I did not do anything bad. So full paper track stats, we had 181 valid submissions that underwent review. What I mean by that is there was a bunch of papers that were not full submissions, so they submitted their abstract, but then they withdrew it or something like this. But 181 full papers that went review process. 28 have been accepted as orals, as you have seen all week, and 84 were accepted as posters, including 31 virtual posters that were presented this morning. Then we had the short paper track review. This had 40 area chairs again, like not quite the same 40 because there was some people that had to drop out and we recruited some new ones. But again, very, very solid team. This round, we did not have additional reviewer layer in the hierarchy, right? So these people did all of the reviews. So I was very, very proud that we needed no emergency reviewers in this round, which I believe never happens ever. So I'm really grateful to these 40 people for their very hard work and their commitment and coming through. On this track, we had 124 papers submitted. 88 were accepted as posters. We had no orals, as you know. And this included 23 virtual posters that were, again, presented this morning. So now, to start with the awards, I would like to start with the Best Reviewer and Area Chair Awards. So these selections were made by the 8 program chairs, and we looked at both the quantity and the quality of the reviews to make our decision. So I'm going to start with the Best Reviewer. This person, I cannot show you anything about the quality because they're anonymous reviews, right? But so I figured I will at least tell you about the quantity. This person had the most papers reviewed, including 6 full papers and 5 shorts. So please give a round of applause to Hoer Karvetek. I don't see you in the room, but please come up to the stage. There you are. And we will do first photos here, and then we will give awards in a second once everybody lines up. We're going to do handshakes, eye contact, smile, like you're not going to kill me. All right, thank you very much. I'll have you stand over here, please. Oops. Thank you for all of the reviews you have done. We really appreciate you. The Best Area Chair actually had the second most papers reviewed, which is a little unusual because the area chairs in the full paper track were not supposed to be reviewing papers. But this person really threw themselves in and did emergency reviews in addition to doing all of the area chair duties. So we really appreciated this. And they end up having, after a while, just the second most papers reviewed total. So please give a round of applause for Yuan Kai Ho. Handshake, eye contact, smile. All right, thank you, Yanka. I'll have you also wait here. Now, I'm going to go show you guys what the awards are, and in the meantime, I will have Vish come say a word about our sponsors who is sponsoring the awards. I don't know if you can go up that way, man. I guess you can.
Good evening, everybody. This has been a fantastic conference, and I would like to thank all the chairs for organizing this, and I've had a great time. I came here to learn. I learned, and I'd like to say there was a lot of passion and just some wise words. How you do anything is how you do everything. With that, I'd just like to invite you all for tomorrow's workshop. We're going to be here from 9 a.m. to 1 p.m. Yeah, in Feathering Hill, sorry. Good catch. And there's going to be food and coffee. Please come. We look forward. And that's it. Thank you.
All right. So the poster awards. The poster award selection was led by a committee led by Jae-Ying Wu. Jae-Ying, where are you? There you are. And we had 4 other members in the committee. So if you are in the room, I don't think we have enough space in the stage for you to come up here, but please stand if you are in this committee. Thank you so much for doing this. Each poster was seen by at least 2 committee members, and they had a scoring sheet, a scoring guideline that was including things like poster clarity, presentation, as well as the scientific content, among other things. So, so let me see. I'm going to do a runner-up and then the best poster. So the best poster runner-up is Iris Vos. For poster number 126, calibration techniques for node classification using graph neural networks on medical image data. Congratulations. Look over there. Thank you. I'll also have you wait over here, please. Yes, Bennett is gesturing wildly. All right. So congratulations. Please stay there, so we can have a group photo in the end. We do not want to anger Bennett. All right. So best poster award goes to Anna Lenny Fry, whose name I'm hopefully not butchering. For her poster titled Local and Global Feature Aggregation for Accurate Epithelial Cell Classification Using Graph Attention Mechanisms in Histopathology Images. Congratulations. Look over there. All right, thank you. We will have you this way. All right, so those are the poster awards. Please stay there so we can do a group photo in a moment. The Best Oral Award Selection Committee. Again, we had a committee. It was led by Jack Noble, and we also had Tolga and Ohal help on this. So if you are in the room, please stand. I see you, Jack, over there. Tolga is there, and Ohal is already on the stage. Now, for these, since we had a fewer number of talks and posters, every talk was scored by every member except for conflicts of interest. And they looked at things like presentation quality, the novelty, technical contribution, as well as the clinical significance. So thank you for doing this work. The best oral runner-up goes to Zijin Gu. Is she in the room? Hopefully she is not back to New York. So her talk was titled Decoding Natural Image Stimuli from fMRI Data with Surface-Based Convolutional Network. Let's see, I do not. She's not here. All right, so we will Photoshop her into the pictures, don't worry about it. And now the best oral of the entire week was Nalini Singh. for her talk titled Data Consistent Deep Rigid MRI Motion Correction. Congratulations. Handshake, smile. Don't jinx it. All right, so we're going to do a group photo, and Bennett will gesture some more. Thank you. Congratulations. Yes, we will get that figured out. Yes, indeed. All right. We also have a medical image analysis special issue. So we had a committee that was doing the selection on this. This was led by 5 PC members. Those who are not here, because these are based entirely on the papers, not the presentations or the posters. So Mirabella, Tobias, Xiao, Martin, and Despina were involved in this, and Mirabella led the charge on this one. They've taken into account reviewer scores, comments, the feedback during the rebuttal stage, as well as the diversity of the authors. So I'm not going to go these one by one because there's 8 of them. So here's the whole list. If you are in the room, please stand up. So we have joint breast neoplasm detection and subtyping using multi-resolution network trained on large-scale H&E whole slide images with weak labels. I'm kind of regretting the decision to read all of the titles now. Vision language modeling for radiological imaging and reports in the low data regime. MS Former multi-scale self-guided transformer for medical image segmentation. Decoding natural image stimuli from fMRI data with a surface-based convolutional network. CP2 image, generating high-quality single-cell images using cell profiler representations. Data-consistent, deep rigid MRI motion correction. And exploring image augmentations for Siamese representation, learning with chest X-rays. So if you are in the room, please stand up so we can do a round of applause. And details on this will be coming in an instruction email over the next week. All right, so those are awards and special selection. I have a couple more slides to thank the organization team. So a special thank you to all of our volunteers. If you are in the room, please stand up so we can do a round of applause. I would like to find Bennett so I can look at him. Right here. He's hiding behind me. That's not weird. All right, so we have a special thank you to Tegan Stewart, without whom it would not have been possible to run any of these events. So she has been at the desk, behind the scenes, all of the places. So we're really grateful. Thank you.
Thank you.
Front and center, you know.
Thank you. All right, and we have had an Oscar-worthy performance, which I would like to share a quick video about. Professor Daniel Moyer, who has been just really, truly everywhere all at once this whole entire week. Without whom this thing would not have worked at all. I believe we have aged him a little bit over the process of the week. We apologize for this. Daniel, come on up, don't be shy. Thank you. This slide deck alone, he has dealt with 35 copies of it. So imagine what he has done all week with all of the teasers, all of the things. We really, truly appreciate it. Thank you. Well done. Look there. All right, so we are almost done with this. So have a safe flight home, everyone. I am excited to report I will not be tracking any of your flights. And so with that, I would like to pass the microphone to Ivana, who's going to be talking on behalf of the MIDL board. Thank you. Thank you for everything this week.
And maybe now I do need Daniel's help. Yes. Okay, a few closing words on behalf of the board. My name is Ivana Yishgum. First and foremost, on behalf of the MIDL board, I would like to thank conference chairs Bennett Landman, Ipe Kogush, and Benoit Devant for organizing a great conference. Thank you very much. Like Ipek mentioned also, we would like to thank program chairs, program board, and the reviewers who have done all the work in reviewing the papers and selecting the program. This work is absolutely crucial, and we hope that the same people will support us also in the future. Thank you all. And then, of course, all other people who are maybe not necessarily visible, but are crucial for having smoothly running conference. Some of them are visible, like Tegan and Daniel. Thank you very much for the activity and all the work you have done, not only now, but also throughout the last year, and all others who are not so present by name. We are also thankful for all the sponsors for supporting the conference. Thank you. And then you have seen this already. Alessa said on Monday, but I want to repeat, MIDL is more than a conference. Annual conference is central and crucial, but we are also organizing events throughout the year. Those are young researcher events, MIDL challenges, and online events like workshops. So might you have an idea for an event, or would you like to organize one, please reach out to us. You can email or contact any of us from the board, or you can email us at board@midl.io. Okay, so MIDL started in 2018. We are happy that we are now closing MIDL in 2023 in Nashville, and we are looking forward to the next conference in Paris. But before I give words to announce a conference in Paris, I would like to say that after the summer, we will be announcing a call for the organization of conferences in 2025 and 2026. So the call will be announced on the MIDL website. Please look there if you are interested, or contact any of us from the board. Thank you again, and I would like to give word to Leo to introduce Paris 2024.
Do I have to give back the flowers now?
No, it's this one.
This one?
Yeah, the one before.
Okay. Yeah, I'm gonna have to give them back.
Full screen, and I will play it. I will play it.
Okay.
Sorry. Okay. So, on behalf of the organization team, we'll be very happy to welcome you in Paris for MIDL 2024. And we are very excited to organize the next edition of MIDL and put together a great program with interesting keynote talks and discussions about all the recent advances in medical imaging and deep learning. The conference will be hosted in Paris, a highly active and evolving ecosystem of academic, industrial, and translational institutions for AI and medicine. And we are waiting for your submissions, and further information will be available on the website very soon, and see you in Paris. We have a little video for you. Without song. Thank you.
All right, we're almost done. I would like to invite Bennett and Benoit to the stage so we can say one final thank you to everyone. You're talking.
I'm talking?
Yep. We voted.
Apparently that was a secret vote. Well, as I said yesterday, I mean, thank you very much for coming. I mean, I was very impressed by the level of involvement that the young scientists in our community have shown during this whole meeting. I think that the field is in very good hands. And again, thank you very much for having been here, for being so active. We've been very lucky with the weather, and hopefully we'll see many of you in Paris next year.
And that's it.
Yay, indeed. Thank you.
Enjoy coffee, posters, flights home.
The pictures, we will post a link on Twitter when they're ready.
I'm going to put them on the WhatsApp, and I'll email everyone, because I'm going to email out like 500,000 photos. So I'll clean up the ones we all and then the best one of each person I'll put on there, put it in the WhatsApp, and I will send it to you an email.
See you in Paris.